Hey everyone, welcome to this 6-hour masterclass on Delta Lake. In this video, I'll be covering the concepts, deep internals, how things work under the hood, and together with this, we will be doing a lot of labs, a lot of practicals to see the concepts we studied in action on Azure Databricks, right? And trust me, this is going to be the most comprehensive video you will ever watch on Delta Lake, right? So before I dive in, I want to give you a quick summary of the topics that I'll be covering, and please watch it in order. So we'll be first starting with the problems with data lakes and how Delta Lake solved those problems. Some examples of it is lack of asset support, lack of update, merge, and delete operations, and data reliability and quality issues. How Delta solved all of these issues, right? So then I'll walk you through the lab setup, the lab architecture, and we'll be doing the lab setup together on Azure, right? And then we'll be performing DML operations, CRUD operations in order to get a feel of how is it to work with Delta Lake, right? We'll then be uncovering the Delta log, right? So all of the magic happens through the Delta log. So we'll be talking about Delta log in a lot of detail and how things work under the hood in the Delta log, right? Next up, we'll be covering concurrency control, optimistic concurrency control, and pessimistic concurrency control, time travel and versioning, schema validation, schema evolution, converting Parquet to Delta, managed and external tables, and one of the most important topics, deletion vector. What exactly is copy on write and merge on read? Then we'll be covering cloning, what exactly is shallow clone and deep clone. Next, we'll be talking about the small file problem, the very popular small file problem, and the root causes of the small file problem. Lastly, we'll be closing this with the optimization techniques, right? So we'll be covering optimize, vacuum, ZORDER, and liquid clustering. Yeah. So I hope you're as excited as I am. So let's get started. So first of all, let's start by understanding why does Delta Lake even exist today, right? Why did it even come into picture when we already had Data Lake, right? And we are going to do this by simply analyzing the pros and cons of Data Lake, right? So some of the things that Data Lake was really good at was that it provided flexible data storage. So if you were to go to a data warehouse, you could only work with relational data. You can work with data that has columns and rows, right? But here the data storage was very flexible. You could ingest structured, semi-structured, unstructured data, and this can be audio, video, images, logs, or basically anything that you wish, right? And data generated from sensors, your web logs, all of this could be streamed into your data lake, and all of this could be stored cheaply at a low cost, right? Inside of something like an S3 or an ADLS. Yeah. And it scaled very well in order to accommodate high volume of data, right? You could basically put in infinite amount of data, and this served a lot of use cases very well. And some of those examples are big data, machine learning, and developing AI application, right? But with all of this, Data Lake still came with a lot of challenges. It came with several challenges, and that was the reason Delta Lake was designed in order to solve these problems. And we are going to go into a lot of details. We are going to discuss those problems in a lot of detail because they are going to form the foundations, right? The first problem was lack of ACID support. Now, what is ACID and why is ACID transaction support so important, right? So as I mentioned to you before, all understanding all of these concepts are really important because they build your foundation. So I'm going to take a lot of code examples and I'll be walking you through all of these, right? So let's get started. So what does ACID stand for? What does it mean? So ACID basically means atomic, consistent, isolation, and the last one is durability, right? So we are going to first study about atomic. What does atomicity mean, right? So atomicity simply means all or nothing. Either you do all of it or you don't do anything, right? Now, how does that apply to our case? Now, let's take a small pseudocode, right? Let's take a small pseudocode and try to understand. So let's say you were transferring some amount from your savings to your checking account, right? From your savings to your checking account. Now your savings account had $1,000 and your checking account had $200, right? And you wanted to transfer $500 from your savings to your checking account, right? Now, what does that mean? That means that this guy should end up having 500 and this guy should end up having 700, right? So let's have a look at the pseudocode for that, right? So we basically read in the current savings, which has $1,000. We then read in current checking, which has $200, right? Now we deduct from saving because we want to transfer $500, right? So what we say is that new savings, it becomes current savings, which is $1,000 minus two, sorry, this is going to be minus $500. Yeah. And this is going to be 500 in turn. Now my account is updated, right? So the savings account is now updated. Now what happens is my system crashes. The checking account, I've not been able to update it so far, right? The system crashes. So what does this mean? That this transaction is lost, it's gone as a whole, right? So what you end up having is that your savings account has $500. Your savings account has $500 and your checking account has $200. That means that $500 went up in the air and it never went back to your checking account. And this is a situation that you never want to be in, right? Because your system failed somewhere over here, and because of that, changes were not reflected in your checking account, right? Now let's see how does an atomic system look like. So what would happen in an atomic system is that you would first begin the transaction. Yeah. Now once the transaction has begun, you deduct the amount from savings, which is 500 is deducted, and the total now becomes 500. Yeah. Now it is added to checking. So the initial balance was 200, you then add 500, which becomes 700, right? And then you finally commit the transaction. Now in between any of these steps, if my system crashes, it is simply going to go to the accept clause and it is going to roll back my transaction. Yeah. So either the whole transaction happened as a whole, both the accounts represent the actual amounts, or nothing happened. The whole transaction is going to be rolled back, right? And this is what atomicity is. Either everything happens or nothing happens. Consistency basically means that rules must be enforced. A transaction must bring a database from one valid state to another valid state. Yeah. So let's understand that with an example. So let's say there is an account which has $100 in place. So this account basically has $100 in place, and then there are two simultaneous transactions going on here. So you see that there are two purchases going on. One is worth $80, the other purchase is worth $60, right? So what these two transactions do is that they basically read in the database at the same time. The first one reads in $100, the second one also reads in $100. Yeah. So they basically go through this line of code. They basically read in the balance. Now they want to find out what is going to be the new balance. Yeah. So they subtract $80 and this guy subtracts $60, which is what we write over here, balance minus amount. Yeah. So this is going to be $20 and this is going to be $40. Now, when both of these transactions are running, there is going to be a transaction which is going to make an update to the database first. Yeah. Now let's assume that this transaction, the first one, the $80 one, is the one that makes the update first. So that means that $20 is the updated balance. Yeah. Now the moment the database was updated with $20, the second transaction goes through and then it updates it with $40. Yeah. So basically runs this piece of code. It updates it with $40. Now, what fundamentally is wrong here is that you made a purchase of 80 plus 60, which is $140, but you only had a balance of $100. Yeah. So this is something that brings your database in an inconsistent state. Okay, so we have the same account which has $100 in place, and then there are two simultaneous transactions going on, which is one is trying to make a purchase of $80, the other one is trying to make a purchase of $60, right? And let's say this transaction first starts and it comes over here, right? It basically does a begin transaction, which simply means that okay, I am going to make changes to the values of the database, right? So now when the second purchase tries to come in over here, what it basically tells him that, hey, I'm going to make some changes, so you will have to wait for me, right? Yeah. So last time what happened was that both the transactions read in $100. Now the difference is that the first one reads in $100, the second one is basically paused. It has still not read in anything, and now the first transaction goes ahead and executes what it wants to. Yeah, so it basically finds in the balance, which is $100. Now it basically, we've put a check in place, right? We put a rule in place which basically checks whether do I have that kind of amount or not. Yeah, so it basically checks that, and okay, we have that amount, so it goes ahead and updates the balance, which is 100 minus $80, which is $20, and $20 is updated and committed. Now, if at all, if you didn't have $80 within your account, it would come here and then it would return to you that you have insufficient fund. Yeah, and your transaction wouldn't take place. Or if any of these operations failed over here, it would simply go to this except clause and then it would roll back the transaction. Yeah, so nothing would take place. Yeah, so now after this transaction, we have simply updated the account balance to $20. Yeah, so now let me quickly actually erase this so that I can walk you through the second transaction. Now when the second transaction comes in, it goes through all of this, it finds the balance. Now the balance is $20, and this statement doesn't go through. The balance, which is $20 greater than equal to $60, which is not true. So this simply returns that you have insufficient fund. Yeah. So basically what this means is that every transaction that we did, both the first one and the second one, it brought the database from one valid state to another valid state. The database didn't end up in an inconsistent or an invalid state. And this is what consistency is all about. The key difference between the two examples is that in the second one, we use transactions to ensure consistency. Yeah, we put in appropriate rules in place to ensure that the relevant amount was there within the bank account. Yeah, and finally, we roll back anything if anything goes wrong. We roll back the transaction if anything goes wrong. So isolation simply is the no interference policy. Yep. So multiple transactions in a database can go on without interfering with each other. Each transaction is going to operate as if it is the only one running, even if other transactions may be running simultaneously. And this means that the intermediate states or the uncommitted changes of one transaction are not visible to the other transaction. So what that means is that, let's say there is a table T and this is in its current state V1. Yeah. Now there is a transaction which basically read in this table, and then it is going on and it is going to make some changes, and then it is going to finally end up in a state called V2. It is going to end up, but it hasn't ended up yet. Yeah. So these are some of the steps that it is going to undertake in order to end up in a state called V2. Yeah. And all of these changes that you see over here are uncommitted right now. Now, if another person, another transaction comes in, and if they want to read this table, if they want to read this table T, it is going to read the V1 state of it. Yeah, because all of the uncommitted changes it is not aware about. So basically, you see that both of these transactions operate independent of each other without worrying about each other. And the way Delta achieved this is by something called optimistic concurrency control. Optimistic concurrency control. And I'm not going to overwhelm you with a lot of details right now, but we are going to discuss how Delta achieves isolation using optimistic concurrency control in a lot of detail going ahead. Durability simply means that once a transaction is recorded in a system, it is going to stay there. Yeah, it is going to stay there irrespective of a system crash, a power outage, or a failure, or anything, right? So consider receiving your paycheck. Yeah. So let's say your current account had $1,000 in place. Yeah, it had $1,000 in place. This current balance basically reads $1,000, and then you got your paycheck, which is worth $2,000. Yeah. Now the new balance is going to be 2,000 plus 1,000, which is $3,000, and finally your account is going to be updated. So your account should be updated with $3,000 after you've received your paycheck. Now imagine that, let's say, some database in some region goes down and this transaction goes for a toss. Now when the system is restored, the old backup is taken and it is restored with that backup. Now that backup doesn't have your paycheck in place, right? So you worked the whole month, now your paycheck is gone just because of some system crash which didn't follow the durability principle. So your paycheck is lost. That means the old backup now shows $1,000 account balance. So this is a durability problem. So how would a system with durability in place look like? So there's a quite a bit of code here, but again, all of them are very simple, easy pseudocode. So again, whenever somebody is going ahead and making a change, we are going to start a transaction. We are going to first write to a transaction log. Yeah. Now think of it as maintaining a ledger of what all is going on. Yeah. You basically keep on writing whatever is going on. So basically, we say that we are going to start a deposit transaction. Yeah. And we also say what are the details of the transaction. So we write to the transaction log that, okay, we are going to deposit an amount to a particular account ID. And then we basically calculate the current balance, we calculate the new balance, we add the amount, and then we update the balance. Yeah. Now, once the balance is updated, we finally write it to the transaction log. And this has the word commit, and then we finally commit the transaction. Yeah. Now if anything fails over here inside the try block, the transaction is rolled back. Now you may of course have questions. What if this whole thing either fails over here or here or here? So let's say we were writing to the transaction log and then it failed over here. Now when the system restarts, the only thing that it's going to check the transaction log. Yeah. So what it is going to see is that, okay, there is something like a start. Okay, let me just change the color. There is something like a start, but then there's nothing after that. Yeah, so there are no details. That means we have to roll back this transaction. Now the second case, what if it fails over here? Over here. Yeah, so it has something like a start and then it has some detail, but again it doesn't have a commit. That means this transaction wasn't committed, it didn't actually go into a database. So again, this transaction is going to be rolled back even if it failed over here. Now all of this goes on, and even if it fails over here, then also it's going to find the same start and detail inside of the transaction log. That means this transaction is going to be rolled back. Whatever changes were made is going to be rolled back. Now if it finally fails after this, when you have the word commit in the transaction log, that means that the data was written inside of the transaction log. Yeah. So the database is then going to finally commit the transaction and it is going to be recorded in the database. Yeah. So this is how durability would look like. And even in cases of failures, you would see that your database would be in a consistent, durable state. Yeah. So with all of these examples, I hope you understand how important ACID properties are. And unfortunately, data lake doesn't have any of these properties. The second problem is the lack of support for update, merge, and delete. And we all know that these are really important operations, something that we do on a day-to-day basis, right? And the problem with traditional data lakes is that the data stored is in immutable files, right? Something that cannot be changed. Those files cannot be changed. And this creates a problem when you want to update or delete that data. Yeah. So let's take an example. Let's say you're running an e-commerce company and then you have a list of customers and then you want to update the customer addresses for some of the customers. Yeah. So let's say that first of all, your data is written to this location and now you want to update customer address at this location. Yeah. So the steps that you need to follow in order to do that is first of all read all of that data. Yeah. And then you need to read and load it into the memory, make all the changes, and then finally write it back. So these are the three steps that you need to do in order to update customer address. Now imagine if your system fails at any of these steps, you are left with inconsistent data. You are left with inconsistent data. Yeah. There also may be a possibility of partial writes at this location, partially written data at this location, which basically means that your data is corrupt. Now, if somebody basically reads the data at this location, they are going to be basically reading corrupt data. Third problem is data reliability and quality issues, right? And a prime example of that is no schema enforcement. Yeah. So let's say you're collecting customer sign up data and today you get a record which looks something like this. Yeah. Which has the name, phone number, email, and phone number. Yeah. Now, tomorrow, let's say you get a record which looks something like this, which has the full name, the key basically looks completely different, full name, contact, and then this is nested inside, and then you have an email and phone number. So the format is completely different from the first one. Yeah. Now imagine you may end up having several of such formats within your data lake without schema enforcement. And when you're writing a query to basically, let's say, find the customer email or a phone number, you may end up writing complex code in order to figure out what the right schema is, right? You may need to write complex logic in order to handle different fields, and this is a very big issue because there's no consistency in your data, there's no schema enforcement. So to quickly summarize, the three problems that we discussed about data lake was: number one, lack of ACID transaction support; number two, lack of support for update, merge, and deletes; number three, data quality and reliability issues, for example, no schema enforcement, right? So Delta solves all of these problems quite beautifully. It just doesn't solve them, but it also comes in with a bunch of very interesting features like asset transactions, time travel, unified batch and streaming, schema evolution and enforcement, and it also helps you see the audit history and all of that, right? So we are going to be going through all of this in detail. So before we get into understanding how Delta solves all of these problems, right, the one that we just talked about, let's first get a flavor of Delta Lake. How does it look like? How does it operate? What are the kind of operations that we can perform? Right? Yeah. So we are going to be setting up a lab environment, and for this we are going to be using Azure. Yeah. And we'll be setting up different kind of services. So don't worry if you don't know anything about it. I'll walk you through the entire process. Yeah. So first of all, we'll be creating a workspace using the Azure Databricks service. Yeah. So first of all, we'll be creating a workspace, and we need some place where we can store our databases, our tables, and all of that, right? And for that, we are going to be using the Unity catalog. Yeah. And for those of you who don't know what Unity catalog is, simple. For now, you can think of it as a place where all of your databases and tables will be stored. Now, in order to store those tables and databases, right, you need some location, you need some storage location. And that is where the meta store comes into picture. So the meta store, you can basically think of it as an object storage, something like S3 or ADLS. Yeah. So in this context, because we are using Azure, we'll be using ADLS, and we'll be creating a storage account. We'll be creating a storage account wherein we will create a container. Yeah, so we'll be creating this container where all of our data will be stored, and we'll name the container metastore. You can name anything, but we'll just name it metastore. So this is the place where all of those tables and databases will be stored, but there needs to be a mechanism using which the Unity catalog here can store data in the container metastore. And that is where another service comes into picture, which is called Azure Connector. Sorry, not Azure Connector, Access Connector for Azure Databricks. Yeah. And what's basically going to happen is that ADLS is going to tell this this guy is that, hey, I'm going to authorize you to be able to access the data in the container metastore. Yeah. So you can now simply access the data that has been stored over here. Yeah. So now when we want to access the data in the metastore, either using the workspace or through the Unity catalog, we are simply going to assume the role of this guy. Yeah. We are simply going to assume the role of this guy, and in turn, this person is going to help us access the metastore. So we finally end up creating the first service, which is Azure Databricks. Then we create a storage account. Then we create a container. After that, we create the access connector. And finally, this metastore needs to know a few things. That linking needs to happen, right? So this needs to know who is the person who can help me with access, right? And it is this guy, the access connector for Azure Databricks. So it needs to know the resource ID of the access connector and the location to which it needs access, right? Which is going to be the meta store. So this is the path, and this is going to be the meta store container path, right? So number 5, we need to perform the linking, right? So once all of these steps are done, we basically set up our lab environment, and then we can start working. Okay, so let's quickly go ahead and create the Azure Databricks workspace. And for that, I'm going to click on create, and we are going to create a new resource group because this is where our workspace, the storage account, the access connector, all of them are going to reside. Yeah. So I'm going to name it as Databricks Delta Lab -RG, and I'm going to follow a similar naming convention. This is -WS. The region is going to be Australia East because I have a lot of resources in other regions as well. I've created workspaces. So to make sure that they don't conflict, I'm going to choose Australia East, but you please go ahead and choose the region that is the closest to you. Yeah. So it is validating some stuff. So meanwhile, we can go ahead and create the storage account. The storage account is again going to be in the same resource group. The naming convention also will keep it very similar. Delta Lab storage account is going to be in Australia East. This is going to be ADLS Gen 2. And for now, we'll select the cheapest option, which is locally redundant storage. And don't forget to put a check here because we want to use Data Lake Storage Gen 2. And we simply go ahead and click on review and create. Let's also click on create over here and create over here. So the last item that we had was the access connector for Azure Databricks. And this is the person who will be assigned, who will be given the authority to be able to access data in the storage account. So let's select the same resource group db delta lab -rg, and this is going to be db delta lab access connector. Yeah, and this is going to be in Australia East. So let's go ahead and create this. So we see now the deployment for the storage account is completed. So inside of the storage account, we need to create a container called metastore. So let's go ahead and quickly create that. So there you go, you have a container called metastore, and in this container, Unity Catalog is going to store all of the data. Now the next part to this is we have to give permissions to the access connector to be able to access the data in my account, in this storage account. Yeah. So what this guy is going to do is that it is going to give permission now, and the role that is going to allow is storage blob data contributor. And because it's a manage identity, we are simply going to select the access connector for Azure Databricks, and this was the one that we just created right now. And we simply click on review and assign. So now we see that the assignment is there in place. That means that the access connector will be able to access the data in the storage account. Now we are waiting for the deployment of the workspace to take place, to complete, right? Okay, so the workspace is now deployed. Now the Azure Databricks workspace is deployed. We created ADLS Gen 2. We created the metastore. We also created the access connector, right? Now, in order to enable Unity Catalog, now we need to do the linking. We need to create the metastore and then provide who is going to be the person who's going to help me with access and what is the path of the metastore. Yeah. So let's go ahead and do this last step right here. So let's quickly go ahead to the workspace. We are going to launch the workspace, and when we head over to the catalog, we see that it only has the legacy Hive metastore and some shared samples over here. The Unity catalog hasn't yet been enabled. So in order to enable Unity catalog, we need to go to account.azure databricks. And we log in with this. So now we'll be able to see that we have an option for the catalog, and there is an option to create the metastore. This is going to be db delta lab metastore. This is going to be in Australia East, and the format of this is the container name at storage account.dfs.core.windows.net. So the container name is metastore. The storage account name is this one. So we simply do this dot windows dot dfs dot core dot windows dot net. Yeah. And then finally we need to put in the access connector ID. So the access connector, we can find it over here. This was the one that we created, and then here is the resource ID. So we simply copy it from here and we are going to paste it over here, and we click on create. So now it is asking me to which workspace do I want to assign this metastore, and this is the workspace that we just created, right? So let's assign the metastore to this workspace, and now we have Unity catalog enabled. So let me quickly go ahead and refresh this, and you see that apart from the shared samples and the legacy Hive metastore, we have two catalogs right now. So this means that a Unity catalog is enabled and our lab environment is now set up. So let's go ahead and create a delta table and perform some operations. So we'll be coming back to this diagram, but let me first go over to the workspace, and then we are going to create a folder called lab delta lake, and here is where we are going to store all our notebooks. But for our labs, we need data, right? So we are going to go to the storage account that we created, which is this one, db delta lab storage account. and we are going to create a container, right? Because we don't want to mess around with the metastore container, because this is going to be used by the Unity catalogs to store all the databases and tables, right? So let's go ahead and create something called lab data, and this is going to create a new container. Inside of this, I'm going to add a directory called shopping invoices, or maybe just invoices. Let's keep it smaller and shorter. So inside of invoices, I'm going to upload all of the files that I have, right? So I have 3 files and I'm going to upload all of them. So these are basically invoices for customer IDs from 1 to 100, 100 to 200, 201 to some large numbers, 99457, right? So don't worry, all of this will be made available in the GitHub repository, so you can download it from there. So now let's move ahead to our lab. Now an interesting thing is that, okay, so we are going to perform DML operations on delta tables. Yeah, so this is our motive, and we want to access the data that is over here inside of the lab data container, right? Now this is not going to naturally have access, right? So the way we access it is, let's say percentage fsls and abfss. This is going to be meta lab data at whatever this is. The storage account name is this one over here. So we copy this .dfs.core.windows.net, right? And I have this cluster already created, and let me also walk you through how to create the cluster over here, right? It's quite simple. So you click on create compute, go ahead and create a single node cluster, because for this lab we don't need a multi-node cluster and you don't want to incur a lot of cost, right? So let's simply choose 14.3 LTS. We don't want photon acceleration, and let's choose a simpler one, something that had lesser memory than 16, which is over here, 14 GB and 4 cores, and set this to 20 minutes. You can even set it to 10 minutes, because sometimes we just leave the cluster running and we incur a lot of cost, right? And then you can click on create compute. So that's how you can create the compute. And now let's come back here. Now let's say if I want to do an ls, let's see what do I get. Okay, so what it says is that invalid configuration value detected for fs.azure.account.key, right? So basically the crux of this is that it is not able to access this data, right? So that is where the concept of external location comes in. So external location are basically locations that are external to Databricks that we want to access, right? And we need to put proper measures in place so that we are able to access that location. And let's first see how we can access this external location. So we go to catalog, we then go to external data, we go to create an external location. By the way, you can also create it using a simple SQL statement, but let's go through the UI and see how this works out. So let's name the external location lab data external, and the way we do it is abfss, and then this is going to be lab data at the storage account name .dfs.core.windows.net. Yeah, so I believe, let's quickly check this. The format abfss, container name, storage account dfs.core.windows.net. Yeah, so that's the path. And then we need a storage credential, somebody whose role I can assume in order to be able to get access, in order to be able to look at the data at that storage location. Yeah. Now, when we created the access connector, it automatically creates a storage credential, and that is what we can use. So we simply go ahead and use that, and we are going to create the external location. Now the external location is created. Now let's go ahead and run this command once again. So now you see that we are able to do an ls on that location, right? So let me also quickly do an ls on the invoices, and we are able to see all of the data that we have put on that location, right? So that is external location. That is how external locations work. Let's go ahead and create a catalog, right? So for those of you who haven't used Unity catalog, think of catalog as a high level container which is going to store your databases and then your tables, right? So I'm going to write this SQL create catalog if not exists, and this is going to be delta catalog, right? And after this I'm going to create a schema, and you can think of schema as a database, right? So this is going to be delta dot delta db, right? So let's go ahead and run this. So now here I should have a delta catalog which is right here, and amongst the default and the information schemas I also have a delta db schema, right? And it doesn't have anything for now, so that is okay. Yeah, so we are going to quickly look at some of the data that we've stored over here, and we're going to use this for creating and operating on our delta lake, right? So I'm simply going to say select star from Parquet, and this is going to be something like this, and let me also do a limit 5. Yeah, so let's go ahead and run this. So this is how our Parquet file looks like. It's basically simple invoices about a customer who made a purchase, what is the gender, age, payment method, what is the quantity, what is the invoice date, and all of that, right? So let's go ahead and create a delta table out of this, right? So let's go ahead and simply write create or replace table, and this is going to be named invoices, right? And as select star from, okay, so this is helping me a lot. I just have to press enter more than doing the actual typing. So this is good, and let's go ahead and run this, right? Okay, great, the table has been created. So let's have a look at the catalog over here, and now we see that it contains invoices, and this invoice is basically your all of the data that we just discussed, and it contains some interesting details over here, right? And we're going to come back to this soon, but before that, let's see the history. And what do I mean by history is that what are the operations that were performed on this table. I was just happy about the about the code appearing automatically, and now it's not appearing automatically. Okay, so describe history cannot be found. Okay, I just misspelled this. So we just created the table using a CTAS statement, right? And that is what you see over here. So it basically tells you that there is a timestamp. On this timestamp, this particular user created this table, and the operation that was performed was basically a create or replace table as select, something like that, right? And then it has all other details as well. Yeah. So this basically tells us that version 0, and this is where versioning comes in, right? This forms the foundation and the basis for versioning. And don't worry, we have a complete section on time travel and versioning, right? So this basically forms the first version 0 of this. Now let's actually also have a look at what is happening behind the scenes, right? So we see that this data is stored in the container metastore in this storage account, the storage account that we provided. And then there is some folder which is named by this long unique ID, and then there is a folder called tables, and this is the unique ID of our table, right? So let's quickly go over here to the storage account, this metastore. Yeah, and so now we go to tables, and then I copy the ID, which is this ID right over here, and we see that there is a Parquet file which is created along with a folder called delta log. So it basically has the data and the metadata. The metadata about the transaction that took place, right? And that is stored in the delta log folder. So this delta log folder basically contains a JSON file which has details about the transactions and a CRC file. We can ignore the CRC file for now because it's for file validation and all of that. So we don't need to worry about all of that for now. So if we click on this, what do we see? So we see all of this, and let me download this file, right? Let me quickly download this file and okay, and let me format this document. So it contains a bunch of stuff, right? And don't get intimidated by this. So the first section is commit info, the second section is metadata, the third section is protocol, and then the fourth section is the operations that we perform, right? And the most important one of this is the last section, the operation that we perform. But I'll still walk you through this. The commit info basically contains the operation that we performed, right? The user who performed this operation, right? And all of that. Now coming over to the add part itself, it is basically the operation that we performed. So we did a create or replace table, and this added some data to the table, right? And that data was added in the Parquet file. It then contains other details. So because our Parquet is not partitioned, it doesn't have any partition value. This is the size. These are the stats, which basically contains what are the minimum values for the column like customer ID. If there's a numeric column, then it would be helpful, something like price and all of that, right? And it also contains the max values over here. So this is very helpful when we want to do partition pruning. Let's say we are reading this file using Spark and we want to do partition pruning. So Spark can basically filter down the files by reading the min and max, right? If it doesn't fall within these bounds, it can simply either include or not include this file. So that is what this operation is for, and it's been noted down in the transaction log. Now let's go ahead and perform another operation. Let's go ahead and do an insert, right? So let's see how the insert statement is going to look like. And it's basically going to look something like this: insert into delta catalog or delta db.invoices, and we are simply going to have a select star from Parquet dot and this one, and this is basically going to be 1 to 100 because we have already inserted from 101 to 200. So let's go ahead and insert the data from 1 to 100, right? So let's go ahead and run this. And we are also going to see the history again. So let me paste this over here. And let's also do some sanity check, right? We are going to do a select main customer ID, max customer ID, and then the count star. What are the total number of records, right? And this is simply going to be from this table, right? So now we see that the insert operation has succeeded. That means it inserted 100 more records. Now let's go ahead and see how the history looks like. The first statement was a create or replace, right? And the second statement was a write through an insert statement over here. And this creates the second version number 1, right? It's 0 index, so that's why it's the second version. Now let's go ahead and run this, the minimum and the maximum. So we are supposed to have 200 records. That's why the minimum is 1, maximum is 200, and the count, the total number of records is 200. So that means that all of the insert and the create statement has happened correctly. So now let's go ahead and have a look at how the delta log looks like. So earlier there was one Parquet file, now there are two Parquet files. We are going to have a look at how these Parquet files look like, right? And let me go ahead and download these two files. So basically I copy this and I'm going to use Parquet tool show, and it resides in my downloads folder. So you see that the first Parquet file wherein we inserted data for customer IDs from 101 to 200, that is what is contained over here in the first Parquet file. In the second Parquet file, this should contain all of the records for customer ID from 1 to 100. So again, let me do Parquet tools, show downloads, and then the part, right? So now you see that this is from customer ID 1 to customer ID 100. Yeah. And let's go ahead and have a look at the Delta log. So we again will download the first Delta log. I mean the second Delta log indexed by 01, and let's open it. Format this document, and we see that this is the second Parquet file that we were talking about, right? The second Parquet file that's been added over here. Yeah, this one. So we see that there are two transactions that took place. First one is the create table. It created a Parquet file, and then it noted that down in a JSON file, right? It noted that transaction down using this add operation. Another operation, when that took place using the insert statement, it also created another Parquet file, put in all of the data over there, and then again noted it down as an insert operation in another JSON file, right? So these are taking place at separate independent transactions. Yeah. Now let's try a few other interesting operations, right? Let's try the update operation. So first of all, let me do a select star from the table where customer ID equals 1. Yeah. And let's see what the quantity is. So the quantity is 5 over here. Yeah. So let me go ahead and run an update statement, update the table, and this is going to be set quantity 10 where customer ID equals 1. Yeah. So let's go ahead and quickly run this. And let me also do a describe history of this table. So we should see an update. Great. We see an update, and this is marked as the next version. Now, let me quickly go ahead and see how this looks like. So the quantity has been updated to 10. That is good. That is what we would have expected. Now, let's see what's going on behind the scenes. So behind the scenes, we see that there were earlier 2 files. Now we see that there are 3 files, right? So this is the latest one that has been written at 6:43. And there is something called a deletion vector, right? And this is quite interesting to understand. We'll have a look at this in details, and let's also have a look at what this file means, the latest transaction. So the latest transaction, let me format this document, and we see a lot of things happening, right? We see a remove, we see an add, and then we also see an add, right? But the fact of the matter is I just updated one row. Why did it even remove something? It removed one Parquet file, it added another Parquet file, and then it added another Parquet file again, right? What were the need for all of this? So there is a little bit of concept behind this, and let's quickly walk through that, right? So let's assume that there was this file called one.parquet, and this basically contained all the records for customer ID 1 to 100, right? Now, whenever somebody wanted to read all the customers from 1 to 100, they would simply go ahead and read this file. Now the situation has changed a little bit, right? The way it has changed is that we want to run an update statement, and we want to update the quantity to 10 for customer ID equals 1. Yeah. So this is what we want to do. So what Delta says is that now anybody who wants to read all of the data for customer IDs from 1 to 100, they just cannot go ahead and read this file anymore, right? Because this has changed. For customer ID equals 1, the quantity has become 10, but this file contains quantity equals 5. So what I'm going to do is that I am going to create two files, right? So we are going to create two files. The first one is one.parquet is going to be as it is, right? And then we are going to create two.parquet and this is only going to contain the record customer ID equals 1 and its quantity is going to be equal to 10. Yeah, so it created another file with just the updated record, and it is going to club one.parquet with something called a deletion vector. Yeah, so it is going to club this with something called a deletion vector, and the deletion vector basically tells that don't read the record where customer ID equals 1. Don't read the record where customer ID equals 1, because again that is going to be read from 2.parquet. So the way the delta transaction log is built, the reason why you see, so basically what do you see one remove. Yeah, you see one remove over here, and that same file is being added over here. Yeah, the first one is the remove, the second one is an add, and then this is the other file. So that is what you see over here. So now let's try to relate it with this. So now when Delta builds the transaction log, what it says is that this file one.parquet, earlier it was being treated as if we need to read the whole file. So now we have to treat it differently. You don't have to read the whole file. So that is why it adds a remove saying that one.parquet cannot be treated the same way it was being treated earlier. Yeah. And then it adds an add. So the way it has to be treated now is one.parquet plus the deletion vector. Yeah. So first it tells that don't treat one.parquet as it was being treated earlier. Yeah. Because it contains the row customer ID equals 1, but the quantity is different. It's not 10. So don't treat it like that. Treat it like this. So for that it adds an add statement with a deletion vector. And then it adds an add again, which basically means that read customer ID equals 1. Yeah, so it makes it very beautiful. It Let's quickly summarize this. So it adds the remove. The remove is for one.parquet, simply saying don't read it as it was being read earlier. You were reading the whole file earlier, don't do that. And then it adds an add one.parquet again, simply saying that read it with the deletion vector. And then it adds an add again with 2.parquet, which only contains customer ID equals 1. So using all of this information, it is able to construct the file. Yeah. So that's the beauty of this. Now let's go back and see what actually happened. So here you see this file. This is without the deletion vector, and this file is with the deletion vector over here. Yeah. And this file over here is the file which only contains customer ID equals 1. And let's verify that, right? Let's verify that. So this is the file over here. Let me download it. We can do a Parquet tool show and download, and then this Parquet over here. So you see that it only contains customer ID equals 1 and quantity equals 10. So this is a very beautiful way of making the transaction log without actually doing the writing and the reading and all of that, right? So when it added a remove, it actually didn't do a remove, right? It just noted it down and logically built up the steps to construct the file. Okay, so let's try a different operation now. Let's try delete. Yeah, so let's do something. So first of all, let me do something like a where customer ID equals, let's say 99, right? So now I just want to see how the record looks like, and the delete statement would look something like delete from this where customer ID equals this, right? Pretty simple. So this is my customer ID equals 99. Let's go ahead and run this. Let me also quickly show you. We have 3 Parquet files, 1 deletion vector, and 3 JSON files, right? So let's go ahead and run this now. If I were to run this, I should get an error now. Yeah, as expected. Yeah, I mean, we should get an empty results, right? Instead of an error. So now we do a describe history of this table and I should see a statement for delete. Great. So now we see an operation for delete and this becomes the most recent version. So now if I refresh this, I still have 3 Parquet files and I have just added a deletion vector, right? So there have been no changes with respect to the Parquet file. And let's go ahead and see the JSON log. Again, let me download it and let's go ahead and open this in Visual Studio. Format document and what has happened. So what has happened is there is a remove and then there is an add. Yeah, quite interesting. So there is a remove for a file which already has a deletion vector and now there is an add. Yeah, so let's quickly go ahead and try to understand what's going on. Yeah, so last time we were talking about one.parquet, right? So we were talking about one.parquet file and this basically contained all of the customer IDs from 1 to 100, right? Now, if you remember, this was updated with a deletion vector. So one.parquet file, a deletion vector was added, and this was for customer ID equals 1. And this was basically to tell that, hey, don't read Parquet file, the one.parquet file as it is, right? Read it with a deletion vector because the customer ID number 1 has been updated. The quantity was earlier 5, now it's updated to 10. And so for that reason, you shouldn't read it like this. You should read it like this with a deletion vector. So that is what was the state. So that is the reason why you see the remove with a deletion vector already. And the add also has a deletion vector. So these both are basically the same files. They are basically the same file and both of them have deletion vector. It's just that the deletion vector has been updated. Yeah. So basically now what happens is we are saying that don't read one.parquet in this condition over here. Read it in a new condition because a delete operation has happened. Something new has happened, right? So a delete has happened. Yeah. So a delete has happened. And in this delete, this Parquet file is supposed to be now read with a deletion vector. And this is going to contain details about both customer ID equals 1 and customer ID equals 99. Yeah. So that is why there was a remove, basically remove over here, basically meaning that don't treat one.parquet as what was defined over here. Treat it as this one. That is why an add is added over here. Yeah. So that is the reason why you see deletion vectors in both the places. It's just that the deletion vector added over here is updated with more detail. Now let's perform the last operation, basically to use one of the Parquet file that I've created, right? So insert into this invoices table and we do a select star from Parquet dot and we will select this last file over here. Yeah. So let's go ahead and insert this file, insert the data that we have here, and let me do a describe history. Yeah. So let's go ahead and do that. And we see that after a delete, there was a write. And let's again see how this is going to look like. So there's going to be one JSON added. And there you go. There is it as we expect. And this should ideally just contain one add. Yeah. So it just contains one ad. We can close the commit info and it just contains one ad. Yeah. And if we go here, there is one file that has been added over here, which basically contains the most recent data. So that is another example. I believe we've covered all of the operation from creating to inserting, updating, and deleting. Yeah. So to quickly summarize, the key concept behind Delta Lake is the use of a transaction layer on top of your data, right? So your data is in the form of Parquet files, and there is a transaction layer called the Delta log, right? And whenever it performs a transaction, it writes all of the data in a JSON file. And this transaction in a Delta Lake is an atomic unit of work, right? It basically groups one or more operations together, and these operations could be, let's say, an insert, an update, or a delete. And the beauty of this is that these transactions either complete successfully or fail altogether. Yeah. And you see that this brings the gist of atomic in all of the acid properties, and that is how atomicity is implemented. So you may have this question lingering in your mind that all of this is good, the data is stored in Parquet files, and there is a transactional layer on top of it which stores data in the form of, which stores transactions in the form of JSON files, right? But let's say when I do something like a select star from this table, how is the latest state of the table that I get to see over here constructed, right? With all of those Parquet files hanging here and there, right? With all of those JSON files, right? How are all of those used to construct this latest state? Yeah. So let's quickly go ahead and try to understand what happens behind the scenes. And this is where I'm going to finally use this diagram. So basically, we are going to have two things that we discuss. This is going to be our data, and this is one example where I've shown partition data, but this can simply be your Parquet file. And then this is going to be the delta log, right? And these are your transactions. These are your transactions. We'll come to the checkpoint and the last checkpoint files a little later in the course. So don't worry about it, be relaxed. So let's take our example, the example that we went through. So the first statement that we ran was a CTAS, right? So it was a create table as select, right? And this led to the creation of the first transaction, which is 0.json. And this created a Parquet file, which was 1.parquet. Yeah. So we are just renaming it to 1.parquet for simplicity. And this contained all of the customers from 101 to 200. The second operation that we ran was an insert. And this again led to the creation of another transaction, which was 1.json. And this created another Parquet file, which was 2.parquet. And it contained all of the customers from 1 to 100. The third operation that we ran was an update, right? And we updated customer ID equals 1. Yeah. So this again led to the creation of another transaction recorded in 2.json. And we've already seen earlier that customer ID equals 1 was present in 2.parquet, right? So 2.parquet was removed because we wanted to treat it differently, and 2.parquet was added again with a deletion vector containing details about handling customer ID equals 1, right? Basically saying that don't read customer ID equals 1 from this Parquet. And another Parquet file was added which only contained details about customer ID equals 1, that was 3.parquet. Yeah. Now the next operation that we did was a delete, and this led to the creation of 3.json. And what we did was that we deleted customer ID equals 99. Yeah. And this 99 is supposed to reside again in this 2.parquet, right? So we again need to change the way we deal with 2.parquet. So what we do is that we remove 2.parquet and we remove 2.parquet with this deletion vector, and we add another 2.parquet with a different deletion vector. Let's say this was dv1 and this is dv2 now. Yeah. So that is what happened as a part of the delete operation. 2.parquet now contains details about handling customer ID equals 1 and customer ID equals 99, right? It's basically saying that don't read customer ID equals 1 and 99 from this Parquet file. Now the last operation was an insert operation, and this again happened in 4.json. The transaction happened there, and this simply created another Parquet file, right? So this simply created 4.parquet, and it contained customers from 201 until some 99,000, some big number, right? Now the question is, okay, we had all these transactions. Now how do I compute the later state, right? And the very simple answer to this is just do a summation. Yeah. How do you do the summation? The way you do the summation is basically this was added and this was removed. So you remove both of this, right? So this is a plus and this is a minus. So these two get removed. This was added, this was removed. So basically this gets removed. Now the only thing that stays until now is this one, which is 1.parquet, this one 3.parquet, this one 2.parquet with dv2, and then 4.parquet, right? So whenever we want to read the file and get the latest state, we basically read in 1.parquet, from where we get all customer IDs from 101 to 200. We read in 3.parquet, where we get in customer ID equals 1. We read in 4.parquet, where we get 201 to 99,000, whatever number it was. And then we read 2.parquet, wherein we read customer IDs from 1 to 100, excluding customer IDs 1 and 99. Yeah, because 1 is read from here and 99 was deleted. So that is the way, that is how simple it makes for processing the transaction log. And you see how beautifully Delta log create these transactions and basically puts them in a way that is very efficient, right? There is a lot of remove, addition and all of that happening, but that actually makes it very efficient because there is no actual writing happening, right? It is basically maintaining all of these states in a ledger. So another interesting question that you may have in mind is that Delta creates a JSON file for every transaction, right? And there could be companies who have millions of transactions in a day, right? And they could have around thousands to five of thousands of tables, right? And I don't even want to go ahead and multiply 5,000 of tables with millions of JSONs being created every day, right? So this requires a lot of compute power in order to read the JSON file. So the question is that how does Delta scale? How does it handle reading massive amount of JSON files, right? So let's go ahead and simulate such a kind of a situation. Now, of course, we won't be creating millions or even hundreds of JSON files, but we'll be creating a few of them to get a rough understanding, right? So let's pick up this insert statement and I'm going to run this in a loop, and let me make this a Python shell, and let's do for I in range 10, and or maybe let me put 50, right? And let's go ahead and run Spark SQL, and let's paste this over here. So we are going to insert this Parquet 50 times, right? So this should add 50 transactions to the table. And let me go ahead and print ith insert completed. And let's go ahead and run this. So now all of the 50 inserts are complete. So let's quickly have a look at how this looks behind the scenes. And we see a lot of Parquet files, which is expected because we added in a lot of data. Let's also have a look at the delta log, and we see something interesting, which is the presence of a compacted JSON, right? Let me load all of this. So what we see here is that a compacted JSON is from the 1st to the 6th, right? The 7th to the 12th, the 13th to the 18th. That means a compacted JSON is being created for every 6 JSON files, right? So I believe it is condensing all of the information. Actually, not condensing, but just picking up all of the information in each of those JSON files and then dumping it over here so that it doesn't have to go through the overhead of opening and closing those files, right? And finally, we see that after 36 JSON files have been created, there is something called a checkpoint.parquet. Yeah. So let's understand what all of these are exactly. So I'll refer this diagram that I created. So over here, we see a situation which is similar to what we just saw, right? What this basically means is that from here to here, all of this data is compacted and it is present in this dot compacted.json file. Yeah. What this also essentially means is that there is no summation happening. Remember, we discussed about summation. Yeah. And that is how Delta computes the latest state, but that is not what is happening here. It just dumps all of the data that it had. So let's say this had, let's say add one dot parquet, and it has add 2.parquet, and this transaction over here, it had a remove 1.parquet. If you were to sum this, then probably 1.parquet over here and 1.parquet remove over here, it should simply go away, right? You should only end up having 2.parquet, but that's not the case. It basically picks up all of the data and dumps it over here. So it's going to contain add of 1.parquet, add of 2.parquet, and then the remove of 1.parquet, and of course all of the transactions and the details, all of the details that is contained in these JSON files, right? So they are all added and they are put over here. Similarly for this one as well, for all of the detail that is present over here, they are added over here. Now imagine you just committed a transaction and you are over here, you just perform this operation. So now how is Delta going to compute the latest state? It is basically going to read, it is going to read this file, it is going to read this file, and then these two files over here. That is how it is going to compute the latest state. Now imagine this is a lot beneficial because it doesn't have to read all of this, right? It doesn't end up reading all of this. So that is how this is optimized for performance. Now after 36 files have been created, you see something called a checkpoint.parquet, and what it does is that it again condenses all of the information from the 0th to the 35th file and puts it over here. Yeah. So let's say you were at this transaction, the only file that you would have to read is that it tries to find out, do we have a checkpoint.parquet file or not, right? If it doesn't have, then it is going to follow the normal process, the one that we just discussed earlier. If it has a checkpoint.parquet file, find the latest checkpoint.parquet file. So that latest checkpoint.parquet file is going to be this one, and then it is going to apply, it is going to read these two JSON files, and then it is going to produce the final state. So that means that you don't end up reading all of this. you don't end up reading all of this. And that is tremendous amount of optimization, right? So that is how Delta handles massive amount of JSON files, right? Simply using compacted JSONs and by using checkpoint.parquet. Another very important point to note is that we see that the gap, right? The gap at which this checkpoint.parquet file is created is 36. If you were to use the open source version, you would probably see this file being created at number 10, right? After 10 JSON files are created, a checkpoint.parquet file is created, right? Now, the reason for this difference, why 36 on Databricks and 10 in the open source version, is simply because Databricks has made several performance optimizations in place so that it can relax the gap and it can create these checkpoint files at a very relaxed gap, right? So that's one of the most important points. And it also varies per cloud provider. So in AWS, this number would be 36. Maybe in Azure, it is going to be some hundred-ish, right? Some hundred-ish. So I believe this gives you an overall idea about how Delta scales and handles massive amount of metadata and JSON files, right? Earlier, we talked about how Delta solves the isolation problem, the I in ACID. And this simply means that it allows several transactions to operate concurrently, to happen at the same time without one transaction worrying about what's happening in the other transaction. Yeah. So it can remain carefree and it can do whatever it wants without worrying about what the other transaction is doing, right? And it achieves this through something very beautiful called optimistic concurrency control. But before we go ahead and understand what optimistic concurrency control is, there's something called pessimistic concurrency control, and these two guys go hand in hand, right? So in order to truly appreciate what OCC, optimistic concurrency control is, let's first understand what pessimistic concurrency control is. And in that sense, we'll be able to understand why OCC was a better choice, right? So with pessimistic concurrency control, the DBMS, the database management system, assumes that conflicts are bound to happen, right? Conflicts are something that will eventually happen and they are likely to occur. And if it's likely to occur, it will occur. Yeah. So to make sure that you understand what a conflict basically is a situation where two or more transactions are trying to modify the same data at the same time, resulting in an invalid state, right? Bringing the database in an invalid state. So we saw several of these examples earlier, right? So if I were to go back to the consistency example that we took, so in the consistency example, we saw that there were two transactions which were trying to update the account balance at the same time. And the one which executed last is going to be the final balance. And this is going to result in an inconsistent state, right? So with pessimistic locking, what we do is that whenever a transaction is trying to make a change to a database, we basically lock that data so that another person cannot come in and it cannot make changes, right? And let's understand that with an example. So let's assume that we have two transactions. The first one is T1. This guy wants to withdraw $100 from this account. And there's another transaction called T2. This guy wants to deposit $400 into the account. Yeah. And let's assume that T1 is the one which starts first. So T1 basically starts first. So the moment it starts, there is an exclusive lock which is placed on this row in the database, right? So there is an exclusive lock which is acquired by T1 and it is placed on this row in the database. So now T1 goes ahead and it basically reads in the balance, it reads in $1,000. Yeah. And because an exclusive lock is acquired by T1, T2 cannot go ahead and make changes. So basically, this will be paused. This will basically wait until T1 has completed. So it basically reads in T1 basically reads in $1,000. It goes ahead and withdraws $100 and then it computes the account balance to be $900. Yeah. Now, the moment it computes this, once that is done, it simply goes ahead and makes an update. So whatever account ID this is, a 45120, and this is going to update the account balance to $900. Yeah. Now, the moment this is done, this lock is released. Now, the moment this log is released, T2 gets a chance and T2 then places an exclusive lock. So T2 is now going to place an exclusive lock on this row in the database. That simply means that after T2 has completed executing, then only another transaction can come in and update this row. So again, it basically what it does is it simply reads in the account balance, which is $900, and it adds in $400, which is $1,300. So it basically goes over here and updates the account balance, and this is going to be $1,300. Now, after this is completed, it simply releases this lock. Now, this lock is released, and the final balance is $1,300. So this is correct, right? There's no problem with this. And what we saw earlier, if you remember, in the consistency example, we also started a transaction over here, right? We started this transaction and we acquired a lock, and then only all of this went ahead and computed the state, due to which the other transaction, the transaction 2, was not able to go inside, right? So we acquired a pessimistic lock. Now this, all of this is really good, right? There's no problem with this. But imagine if locking was not in place. If locking was not in place, what would have happened? Both the transactions T1 and T2, they would have come in, they would have read $1,000, and this guy would have subtracted $100. It would have computed $900. This would have added 400. This would have computed 1400. And whichever was the one updating this last would be the final balance of the account. Now, of course, there's a chance that you could have more money, but there's also a good chance that you'll end up having less money. Yeah. So pessimistic locking helps us achieve consistency. It maintains the correctness of the database. So what are the problems? Why don't we want to use pessimistic concurrency control? Now you see that T2 had to wait. It had to wait till T1 was completed. And imagine if you have millions of transactions taking place, then this whole system is going to come to a halt, right? This is not going to be meaningful anymore, because you would have to wait endlessly in order for few of the transactions to complete, and then I would get a chance, right? So that is where the problem comes in. It makes your system slow, and for this reason, we want to use optimistic concurrency control. With optimistic concurrency control, transactions do not obtain locks when they read or write. And that's the beautiful part, right? So the name optimistic actually comes from the fact that it assumes that conflicts are very unlikely to occur, and this is quite just the opposite of what pessimistic concurrency control assumes, right? So this guy assumed that conflicts are very unlikely to occur, so I don't need to think about it, right? And if at all it occurs, the conflicting transaction is the guy who's going to be retrying, right? So let's understand this with an example. So let's take the same two transactions, right? T1 basically trying to withdraw $100 and T2 trying to deposit $400. Yeah. And these two transactions go ahead and read in this row at the same time. So T1 basically reads in $1,000 to be the current balance. T2 reads in $1,000 to be the current balance. And the reason why they are able to read this row at the same time is because, as I discussed earlier, there is no concept of locks in optimistic concurrency control, right? So because there is no concept of locks, this row over here is not logged by either of these transactions. They both can go in and read in the data over here at the same point in time, right? So they go ahead and read the balance, and along with that, they also read in something called version number and timestamp. So version number is going to help track changes within a table. So it reads in version number 1, and then it reads in something called TS1. Let's call this TS1. So this is going to read in 1 and TS1. Now it goes ahead and does all of the calculations, right? So this is going to compute, do a subtraction of $100, and it is going to compute the final value, which is $900, right? And this is going to add $400, and it is going to compute the final balance, which is $1,400. Now both of these people are going to try to commit. Both of them are going to try to commit. Yeah. Now we need to understand that there is going to be one person who is going to commit first. Yeah. So let's assume that T1 is the person who commits first, and there is a procedure, there is a way in which the commit is going to happen. So the way it will happen is it is going to check what is the current version number. It reads in that the current version number is 1, and it sees that the version number it has is also 1. Yeah. So that means that I am working on the latest data. There is nobody who came in while I was working and made changes to the table, right? So I can simply go ahead and I can make the addition, update the balance, right? Because I was working on the latest data. So now what happens is that it goes ahead and add this row, which is A45120. This is going to be 900, and it updates the version to version 2, and this is going to be TS2. Now this person, transaction T2, who was also trying to commit at the same time but actually ended up committing second right after this happened, what it sees is that it reads the version number. The version number that it finds is 2, but the version number it has is 1. So this simply helps it understand that there is a person who came before me, before I was trying to commit my transaction, and actually made changes. And this means that I was working on stale data. I need to read in the latest data, make the changes, and then actually update the table or add a row to the table, right? So what it does is that it will simply fail this transaction because it was not working on the latest data. Yeah. So now what happens is T2 now reads in the latest version of the table. So it reads in the balance 900, the latest version is 2, and it reads in the timestamp TS2. It goes ahead, applies the operation, which is $400, computes it to 1300, and now it goes to commit again. So it goes and commits again, and it follows the same procedure. So it checks what is the latest version. The latest version appears to be 2, and the version it has read is also 2. That means there is nobody who came in while I was working and make changes to the table, right? So that also means that I was working on the latest data, so I can make updates, make a row addition to the table. So that is what it does now. And let me first just remove all of this. So it goes ahead and it makes an update to this table. It adds in a new row, it updates the timestamp, and this is called TS3. And this is how the table ends up in the correct state. Yeah. Now imagine that T2 was still working and there was a transaction called T3. It wanted to read the latest state of the table. And let's imagine that this row was not yet committed. T2 was still working. What would happen? T3 would simply go in and read the latest state. It would read in $900. So this means that even though T2 is working, T3 is not affected, right? So all of these transactions can go on and on simultaneously. And there can be millions of such transactions. And that is where the beauty of optimistic concurrency control lies. Yeah. And it also allows T2 to fail and retry. Yeah, so it gives us that flexibility. So to reiterate, with optimistic concurrency control, we have completely avoided locks. Yeah, and the key to this is that if I'm performing operations, the other transaction isn't or doesn't need to be aware of whatever I'm doing, right? They can simply read in or they can simply fail and retry, right? My operations are not visible or affecting other operations, other transactions. Yeah. And this allows, as I discussed earlier, it allows very high levels of concurrency. And this is particularly beneficial in read heavy systems. Yeah. it is beneficial in read heavy systems. So if you were to think about it, optimistic concurrency control, basically the foundations lie on the fact that conflicts are very rare. They will most unlikely happen, right? They are not bound to happen. If they happen, the conflicting transactions are going to retry. Yeah, that is the foundation of optimistic concurrency control. And when do conflicts happen? Very rarely. In those systems where write do not happen a lot. Yeah, so in those systems which is read heavy, so this is very beneficial for read heavy system. It's very good for read heavy systems. So I believe this helps you get an overall idea and an in-depth understanding about how Delta solves the isolation problem quite beautifully using optimistic concurrency control. Now let's go ahead and talk about time travel and versioning. So I believe in the previous few examples that we've seen, right, we did statements like describe history of a table, and it showed us several versions of that table, right? So versioning basically helps us track different stages of the table, right? So let's say you had a table, you made an update to the table, now it became a new version of the table. Let's say you made a delete, so that becomes another version of the table, and you can go to any of these versions back in time and you can restore your table to that version. So going back in time and restoring it to any other version is basically time travel, right? So we are going to have a look at all of this through a lot of examples. Let's go ahead and create a table first, right? And we are going to perform all of the operations on this table. So I'll quickly copy this path and create a table using the data that is there in this Parquet file. So let's go ahead and do a create or replace table as then actually the name of the table, delta catalog dot delta db dot invoices underscore tt time travel and versioning as select star from Parquet dot this path, right? So let's go ahead and create this. Okay, now let's have a look at this table, how this looks like. Delta db delta catalog dot delta db dot this table, right? And let's do a limit 5. Okay, so this is how the table looks like, and I believe we've seen it a couple of times already, right? So now let's go ahead and perform a few operations on this table. So let me go ahead and do a delete first, right? So we'll do delete from this table where customer ID equals 1. So this row that you see over here is going to be removed. Let me go ahead and run this. Okay, great, that succeeded. We are not going to verify that now. Let's go ahead and also do a few more operations. So we'll do update this table, set quantity equals 25 where customer ID equals 5, right? So we see that the customer ID 5 over here has a quantity equals 1, and I want to update that quantity to some random number 25, right? Let's go ahead and do that. Okay, that works. And the final statement we'll do is insert into this table and select star from we did it from a Parquet file last time, right? So we inserted customer IDs from 1 to 100. Let's do from 101 to 200 now. Yeah. So now let's verify all the changes very quickly. So the latest version of the table would be this one, right? If I do a select star from this table name, I would get the latest version of the table. So if I were to do select star from this table where customer ID equals 1, there should be no rows. Let's go ahead and run this. I didn't get a row. That means the delete worked fine. Now let me check where customer ID equals 5. So the quantity is 25. That means the update also worked fine. And then finally, let's check how many customers have been inserted with customer ID greater than 100. And the last time we did this, we saw that there were total 100 affected rows. So the count star should give me a count of 100. Perfect. Let's have a look at the history of the table. Yeah. So I'm going to write describe history of delta catalog dot delta db dot invoices ttv, right? So here we see that there are four versions of the table, right? The first version was created when we did a create or replace table, right? This statement right over here. So this created the first version. And then we performed three operations. The first one was a delete, where we deleted customer ID equals 1, then we updated customer ID equals 5, and then we wrote in 100 additional records from 101 to 200, right? The customer ID. So that created four versions. The 0th version, another operation was applied, the first version, another operation was applied, and the second version, and then so on, right? So these are essentially the versions that get created, and using those versions, you can go back in time, right? So let's take an example. So if we do a select star from this table where customer ID equals 1, we won't get any row back, right? We know that. But let's say we want to go back in time and we say version as of, we know that in version 0, it contains the customer ID equals 1 row, right? So let's do this. And there you go. You see that the row where customer ID equals 1 is returned because this time we picked the table where version was 0, the oldest version over here. Yeah. And you can also do this by selecting the timestamp instead of the version number. And the only change that you need to do is select star from this table, timestamp as of this, where customer ID equals 1. That should work, and it gives you the same results. So you can either use version as of, or you can use timestamp as of and go back to any of the versions back in time, right? So here we just did a select statement. Right now, what if you actually want to restore the table to this version? How do you do it? Yeah, so the way you do it is by actually using the restore command. Yeah, so you write restore table delta catalog to version as of 0. You can also use timestamp as of 0. Timestamp, sorry, not timestamp as of 0, but timestamp as of whatever timestamp you have over here. You can do this as well. But let me comment this out for now because we cannot run both of them at the same time. So now instead of doing this, instead of referring to version number 0, let's remove this and then do a where customer ID equals 1. So in this case, now we should get that row because our table has been restored to the 0th version. And there you go. So you see that the row where customer ID equals 1 is returned. And let's also have a look at how the history of the table now looks like. Great. So it tracks every operation. So write was our last operation, and after write we did a restore. So it tracked that operation. Yeah. And it was restored to version number 0, and that is also tracked over here. Yeah. Now let's say that you want to restore the table to a particular timestamp. Yeah. So let's take this example. We want to, there's a particular version that exists at 931, and that version is version number 2. Another version exists which is at 957. Yeah, and this version is version number 3. Now let's say if I enter a timing which looks something like this, which is 935, what is going to happen? Because a version doesn't exist at 935, right? So let's say if we were to do something like select star from this table, timestamp as of this timing, what would happen? So you see that it gives us some results. Yeah, it gives us some results. So what it essentially does is that at 935, right? Let's say this is 931. At 935, it looks whether there is a version which exists at that timing or not. If there is a version, it will basically pick up that version and give it to you. if no version exists, it is going to find what is the latest file that existed before this time. And it is going to find out that the latest version was version number 2. So that is why it gives version number 2, which is the file that resided at this point in time, which is 931. And we can verify that. We can verify that by having a look at this file and checking the customer ID, which is where customer ID equals 5, because you remember that in version number 2 we updated the quantity to be equals to 25. So this should give me 25 if whatever logic we are trying to make up right is correct. So let's have a look at that, and you see that the quantity equals 25. Let me also run it with the latest table, and we should get different results. This should give us quantity equals 1 because this is based out of version 0 as we've seen, right? But this is based out of version number 2. Yeah, so I hope this helps you understand that if you enter a timing which is not present in the history of the table, it does that mapping by finding out the closest file before that particular timestamp. So now that we've seen all of the action in SQL, let's go ahead and try a few things using PySpark data frame. Yeah. So I'm going to write a %Python, and this is going to be df equals spark dot read dot parquet. Okay, this is not going to be Parquet, this is going to be table, and this will be delta catalog dot delta db dot invoices underscore ttv, and I want to read in a particular version, right? So let's say we want to read in version number 1, and this is simply because it doesn't contain customer ID equals 1. Yeah, just to make sure we are reading in the right version. So the way we specify that is by doing an option, and we specify version as of, and this will be 1, and let me do a display with a filter df.filter, and for that let me first from PySpark.sql sql.functions import column, and I will do a column, and this column is basically going to be customer ID equals 1. Yeah, and this should not return to me any record. So it basically didn't return to me any record, and that is why it read in the correct version. Now let me also repeat this with version number 2, and this is going to show me that quantity equals 25. Yeah, so customer ID equals 5, and this is going to be version number 2, and let me add in a %Python here. So this gives me quantity equals 25. So this is how you would read tables, read versions of tables using Spark data frames. And you can also replace this with something like a timestamp as of, and let me again read in this one for version number 2. So this should also give me the same result. Okay, there's some %Python. Great. The quantity equals 25, and it gave me the same result. So now let's talk about schema validation. And before we talk about schema validation, in order to set the context, let's talk about two interesting things called schema on read and schema on write. Yeah. So in order to understand schema on read, we'll take the data lake context. Yeah. So inside of data lakes, what we can do is we can simply dump in any kind of data which is in any kind of format, and it basically goes in and resides in this data lake over here. Now it is kept in this data lake, and it can reside for as long as it wants, and when we want to read in data, we simply go ahead and pick up that file and read that file, and then apply the schema. So the schema application process happens after the data has been stored in the data lake. Now, if you look at schema on write, what basically happens is that let's say these are your incoming records. First, it is checked whether the schema matches to your existing schema, right? So let's say there is an orders table, it has 5 columns, and those 5 columns have some data types, right? So in order for these records to be ingested or to be able to reside in the data warehouse, these records have to match those 5 columns and the 5 data types. Yeah. So the application of schema happens earlier before ingestion. So this is where ingestion happens. Before ingestion, the application of schema happens. Yeah. So this is schema on write. Schema on read is basically the ingestion happens earlier and then the application of schema happens. Now, the reason why this is problematic is because let's say on some date you got the orders file and it looks something like order ID, the amount, and then let's say the date on which the order was placed. And let's say after a month, the order file looks completely different. This is the order ID, and then this is going to be the order details, and then there is going to be something like the amount and the date residing inside of order details. And now this is also ingested. Yeah. So different kinds of files with different kinds of schemas gets ingested. Now when you want to read orders, you get confused whether this is the right schema or this is the right schema. And there is going to be several problems. So for example, if you want to find out the orders, some of these files you'll be able to easily read it, but in other files you'll have to do some transformation, basically pull it out from here. So the schema is not consistent, it is not well maintained over here. So that basically helps you understand what schema on read and schema on write is. And delta is schema on write. So that helps you enforce schema. It validates the schema before making any data come inside of a delta table. So let's understand schema validation with example. Yeah. So I'm going to create a table that we are going to specifically use to understand schema validation. And for that, let me simply do create or replace table delta catalog dot delta db dot invoices underscore sv for schema validation. Yeah. So the column that I'm going to have is customer id. This is going to be int, and I'm going to add a constraint. So this constraint is going to be not null. My customer id cannot be null because it is the primary key of my table. And then it is going to have invoice number. This is going to be a string. Then we are going to have quantity, which is going to be an integer. Then we are going to have price. This is going to be a, let's say, float. And we are going to have invoice date, and this is going to be a date, and this is going to be the definition of our table. Now we have to also insert some data inside our table, right? And we are going to do that using the insert statement. So insert into this table, and we are going to use the select statement. So select star from, we're going to use the Parquet file that we used earlier. This contains all the customers for customer IDs from 1 to 100 from Parquet, and this is going to be the file. And I'm going to select the relevant columns only because as we've seen earlier, it has a lot of columns. So it is going to be customer ID, invoice number, quantity, price, and invoice date. Now let's go ahead and run this. Let's also get a feel of the data. Let's see how this looks like. Let me do a limit 5. So now you see that we have the table created, right? And just to do a few checks, this table should have customers, customer ID from 1 to 100 and a total of 100 customers. customer ID and the count star from this table should be 100 and 100. Okay, so now that we have the table set up, let's understand column order validation. Yeah, so let me quickly write down this heading: scenario 1, column order validation. Yeah, so in order to do this, we are going to run an insert statement. You're going to insert into the table, and we are simply going to do it through a select statement. Select these columns from values, because we are going to insert only one row, as t, and this is going to be all of this. Now the customer ID is going to be a large number, 99,999. The invoice is going to be 1234 I12345. Quantity is going to be 10, price is going to be 100, and invoice date is going to be 2025-0101. Yeah, now before we do the insert, let's see how this looks like. So this basically looks like the first customer ID is 99,999, and all of the rest, right? Quantity is 10. Now what I want to do is interchange the order. Now because quantity and customer ID are both integers, I want to interchange them so that there is no conflicting data types, right? Now let's run this. So the first column now becomes quantity, which is 10, and customer ID becomes the third column, which is 99,999. So what I would desire is that if the insert statement happened correctly, a new row gets inserted where customer ID equals 99,999. Yeah, and quantity equals 10. So let's go ahead and run this. And meanwhile, let me also write select star from. Okay, so this completed successfully. Let me go ahead and write this, where customer ID equals 99,999. Yeah, so this is what we wanted. A row which has customer ID 99,999, that should be in the table because we just ran an insert statement. So let's go ahead and run this. What do you think? Would we find that row there? Okay, so that row is not present there. Where did it go? What happened? What just happened to my table? So what we see over here is, let me go ahead and run this again. What we see over here is the first column was 10. So what actually happened was that it took in the columns by position and it mapped to the customer ID column. 0, column number 0, column number 0. So I'm going to take in the value from this column which is at position number 0 and put it inside customer ID. Yeah, so this is something called column matching by position. So let me go ahead and see if we have where customer ID equals 10. So we already had customer ID equals 10, right? Because we inserted data from 1 to 100. So that means now after this insert, there should be two rows. There you go. So we have two rows, which is customer ID equals 10 and invoice number 12345. Quantity is 99,999 and the rest of what we inserted. So what insert did is that it executed the insertion by matching columns by position and not the names. And that is why you see what you see over here. And this actually corrupts your data. So never use an insert unless you're very sure that the positions will always be maintained. So let's see what is going to happen if we reorder the columns and insert that data into our table using a merge statement. Is it going to behave any differently? Yeah. So let's try that out. And the source data that we are going to use is all the customer IDs. Actually, not all the customer IDs. The customer IDs from 101 to 200, and I'm just going to take 5 of them. Order by customer ID descending, limit 5. So this is going to give me 5 customer IDs from 196 to 200. Yeah. So let's go ahead and write the merge statement. Merge into this table as target using this source table. Using this source table, the join condition is going to be on target.customer id equals source.customer id, and when not matched, then simply insert star. So these 5 rows, they are not going to match with the existing data that we have in the table, right? Because the existing data is for customers IDs from 1 to 100, right? So these are not going to match, and they are supposed to be inserted in the table. Yeah. Now what happens if we run this statement again, right? Again and again. So the first time it gets inserted, the second time you run it, it is going to match this statement. Because of this statement, target customer id equals source.customer id, they are going to match, right? Because 196 to 200 already resides in our table. So in that case, what we are going to do is that when matched, then update set the following columns, right? Set customer id dot customer id equals source dot customer id, target dot invoice number equals source dot invoice number, the quantity target dot price equals source dot price, and the final one, target dot invoice date equals the current date. So if they match, what we are simply going to do is we are going to keep all of the columns the same. We are just going to update the invoice date. Now let's go ahead and make the change. We are going to swap the columns over here. Quantity is going to be the first column and customer ID is going to be the third column, exactly same as what we did over here. Quantity was the first column and customer ID was the third column. And let me also do one change, because this is coming from this Parquet file. Price over here is a float, right? So this should also be a float. Cast this as float. Yeah. So now let's go ahead and run this. So while this runs, let me write some SQL to quickly validate this. Select star from this table where customer ID greater than 100, right? And the only customer ID is greater than 100 in this table should be these ones, right? These 5 records. So we run this, and there you go. So you see that the customer IDs from 196 to 100 have been returned. That means that the merge statement ran correctly. It was able to identify which columns to match. Now, a very important point to note is that insert the matches columns by position. The 0th position is going to be matched to the 0th position from the source. But what merge does is that it matches column by name. It finds the right name even if they are not ordered correctly, and then matches them. And that is the reason why this worked. Yeah. So now let's go ahead and run this once again, right? So that it comes to this clause and then it just updates the invoice date. Yeah. So let's go ahead and run this now. And ideally, this is the only column that should change. Okay, let's order this from 200, and there you go. You see that this is the only column that changed, while all the other columns are just the same. So merge seemed to work just fine. So now let's try to understand how Delta does data type validation, right? How it does data type validation. And this is going to be scenario number 2. So let me quickly write that down. Data type validation, and we are going to test this by writing an insert statement. So we are going to say insert into delta catalog this table, and the values are going to be, let's say the customer ID is going to be ABC, invoice number is going to be I45678, quantity is going to be 10, price is going to be 98.75, and the invoice date is going to be 20250101. Yeah. Now if I were to ask you whether this piece of code will run or not, I think the obvious answer would be no, because the data type for customer ID is integer, but what we are trying to feed into it is a string. So let's go ahead and run this. And as you expected, it didn't work because this is string and it tried to convert it to integer, but it didn't work. Yeah. But now let's go ahead and do something different, right? So let me go ahead and write this customer ID, which is 99499. Now what do you think? Will it run? Let's go ahead and run this. Okay, there you go. So it seems that it ran. Let's do a select star from delta catalog. So the intelligence sometimes works and sometimes doesn't. It's completely dependent on its mood, where customer ID equals this, right? So you see that there is a row 99499 and it contains the exact same detail 98.75 and quantity. So the question here is, why did this work at all if this didn't work? The reason why this worked is because what Delta does is that it puts in effort to convert it into the form that it actually exists in the table. So in the table, it is in integer form. It tries to convert it to an integer form. Yeah. If the conversion happens successfully, it inserts the data into the table. If the conversion doesn't happen, then it throws an error. So that is why you see the error thrown over here is that string cannot be cast to int. Yeah. So it tried to cast it, but it cannot cast it to int. And that is also the reason why this 20250101, this is string, but the data that we have over here is date. So it casted string to date and then inserted the data in this table. Yeah. But this also makes sure that we just cannot dump in any garbage data. So that check is there in place. So let's have a look at another scenario, which is column name validation. Yeah. So, okay, it seems I missed writing column name validation here. Column name validation, and this is going to be number 5, number 6, and this is scenario number 3, right? So let's go ahead and add a heading, scenario number 3, column name validation. And the way we are going to test this is simply I'm going to copy the code that I use for column order validation, and we are first going to test this with an insert statement. So let's make sure that the order is the same, because there's no point changing the order, right? We've already tested for order. And let's go ahead and change the column name. This is going to be as QTY. So now we've changed customer ID to C underscore ID, quantity to QTY. Yeah, let's go ahead and run this now. So if this SQL ran correctly, you should see something like a row which basically contains customer ID equals this number. Okay, there you go. So you see this row where customer ID equals 99,999 and all of these other details, right? So the reason why this worked, even though the column names are different, is because of a reason that we already discussed some time back, right? So it does column matching by position, and it doesn't matter whatever in the world the name that you decide to put over here, it doesn't matter, and that will be of no effect. So that is the reason why this worked. Now let's try the same thing with a merge statement. So last time we used this data over here. This basically contained customer IDs from, okay, the order is changed. Let me get this back to the same order. So it contains customer ID from 196 to 200. Let me change it to have from 101 to 105. Yeah. Now let's go ahead and insert this data. And before actually we run this query, we want to change the name of the columns, right? So we want to change this to QTY. Uh, where are the other places? C underscore ID, underscore ID, QTY, right? So now that we've made all of the changes, right? Let's go ahead and run this and see what happened. So if this statement runs successfully, what we should see is when we run something like this, right? If we run something like this, I should see 5 more rows. So I should see these rows as well. So let's go ahead and run this now. So now what it says is cannot resolve customer ID in insert clause given columns is source.c underscore ID. So the reason is pretty simple and it is again something that we already discussed. So think about it for a minute if you're not able to recall why it failed. So the reason why it failed is simply because merge does column matching by name. So it looks at the target table, it takes up a column, let's say customer ID, it looks up for that exact column in the source table. Okay, do I find customer ID in the source table or not? If it finds it, then it is going to dump all of that data in the target table. But if it is not able to find it, it is going to fail. So it is quite a robust statement. So now let's have a look at another scenario, which is nullability validation. Yeah. So let me quickly add in the heading scenario 4 nullability validation. And here by nullability, I just don't want to talk about nullability, but a few other things as well. So let's have a look at this. Insert into delta catalog dot this invoices table values. We have how many columns? 1 2 3 4 5. So that's going to be 5 nulls. And if I were to just copy this and paste it 5 times, and if I were to ask you whether this will run or not, obviously you would say that this won't run. So the reason why it didn't run is because the not null constraint violated for column customer ID. So we had a constraint over here, customer ID int not null, whatever customer ID we insert, and for now there can be duplicates, right? But they shouldn't be null. Yeah. So that constraint was violated over here, and that was the reason why it wasn't inserted. So if we run the same statement, right? If we run the same statement, inserting some random number 78912, this will work. And as expected, this works. So the point that I'm trying to make over here is not just nullability validation. It's about constraints, validating the constraints that we've put, right? So we put in a constraint which is not null over here. We can also put in constraints like, for example, the price should be greater than 0, the quantity should be greater than 0, something like that. We can put in rules over here, and whenever data is inserted, all of those rules would be checked for, and this would make sure that the data that is getting inside our tables are correct, they are accurate. Now let's have a look at the last scenario, which is extra column validation. What happens if in my source, the data that I'm trying to insert, it has extra columns and the target table does not have those many columns, right? So what is going to be the case? So this is going to be scenario number 5, and this is going to be extra column validation. So let me copy some code. I'm going to copy the code that I use for column order validation, and I'll comment this out for now, and let me add in an extra column, right? And this is a dummy column. Let me name it as customer type. So you see that all of the columns over here are intact. And actually, let me also correct the orders. Customer ID should be over here. Yeah. So the orders have been corrected now. And let's also change this, right? So the orders have been corrected now, and we have an extra column which is customer type. Now let's see what is going to happen. So you see that this didn't work. It says that a schema mismatch detected when writing to the delta table. Now let's go ahead and try this with a merge statement. So if I were to copy this merge statement over here, and let's go ahead and run this. Actually, let's change the source data a little bit, right? So now I'm going to take up all of the customers whose ID is between, where customer ID between 150 and 155, and I want the order of columns to be the same. So let's go ahead and run this. So this gives me all the customers whose ID is between 150 to 155, right? So let's go ahead and paste this over here, and let's also add in an extra column over here, which is VIP as customer type. Now these rows are not in the table, right? So it should go to this clause, when not matched then insert star. So all of them should be inserted, and because I want to test that particular case right now, let me just remove all of that for simplicity. So let's go ahead and run this. And actually, before I run this, let me show you that there is no record. Select star from this table. This would give me no record. Now let's go ahead and run this now, and you see that it succeeded. Let's run this. Great. So I see all of the records from 150 to 155. That means that the insert statement has worked correctly. So it tries to match the columns by their names, and if it's not able to find a name, so basically it started with the target, it searched for all the 5 names, it was able to find them, and then it just went off, right? It succeeded and the operation completed. Yeah. So the merge operation is actually quite a robust way of doing things, right? It was able to handle a few other issues earlier as well. Now let's understand what schema evolution is, right? So schema evolution is the ability to handle changes in schema without having to completely rewrite your table, or without having to rewrite the underlying data. Yeah. So when I say ability to handle changes, what I mean is that, let's say if I have a table, if a new column comes in, I should be able to accommodate that new column. Or let's say if I have a column which is of type int, let's say order ID is of type int, and for some reason I'm getting a lot of orders and my order ID has gone beyond the range of integer, and I want to change it to long or big int or something like that, right? So I should be able to upgrade my data type to another type. So all of that flexibility should be allowed. So we are going to have a look at 4 scenarios. The first one is adding new columns. One is the manual way, the other one is the automatic way. So we'll be having a look at both of them. The second one, as I discussed, is widening of data types. The third one is nested structure evolution. The last one is column position changes. If for whatever reason I want to reorder the columns in my table, there should be enough flexibility to allow me to do that. Let's go ahead and understand the first scenario, which is adding new column. Let me first quickly write in scenario number 1, which is adding new columns. And for this we are going to create a brand new table, and for that I'll copy the code from schema validation. So let me just remove this line, change this to SE for schema evolution. Quantity is going to be removed because I want to keep minimal number of columns and minimal number of rows as well for this example. So let me do a where customer ID between 1 and 5. So we'll insert 5 rows into this table, and let's also remove quantity. Let's go ahead and run this. Quite simple. We've got what we expected, and let me put this over here. Let's go ahead and run this. Okay, my bad. This should be SE. Let's go ahead and run this now. And let's quickly validate that the table looks just as we expected it to look like, and it looks as expected. Yeah. So the table is set up now. Now let's go ahead and add a column to the table. So we are going to run an alter table invoices.se add column, and the column that we are going to have is, let's first see how many columns are there, like what all columns are there. So for that, let me run a select star, and we see that there are, okay, we'll use the quantity column that we just dropped. We didn't want to select that, so let's use that for now, and this is going to be quantity integer. So this column has been added to the schema of the table. Now I want to insert a few more rows, and this time it is going to be with the quantity column, and let's insert rows from 6 to 10 now. So let's go ahead and run this. Let me copy this to see how the final table looks like. So the final table should look like 5 columns in place, with these rows not having the quantity data. They should all be null, and the one that we inserted right now, they should all have non-null data for quantity. Let's run this, and there you go. As we expected, we see non-null data for quantity for the customer IDs that we've just inserted, and null quantity for the one that were inserted earlier. So you see that we had to run an alter statement over here in order to accommodate this new column that was coming in. Now, what if you want to do this automatically? Although there can be situations where we want to go ahead with this approach, sometimes we don't want to go ahead because we don't randomly want any kind of data to come in and then sit in my table, right? But let's say for this situation, what if you want to automatically accommodate a new column? So for that case, you need to set this property to true, and this enables schema evolution. So let's go ahead and run this now. So this is enabled to true, and let me run another insert statement, this time without doing an alter, without running an alter table command, but I will add another column. So let's see which column do I want to add. So let's add payment method. So let's add payment method over here, and this is going to be 11 to 15, and this is going to be inserted in the table. The table had how many? It had 1 2 3 4 5 columns. Now if this works well, we are going to have 6 columns, right? And the payment method column is going to be populated only for customers IDs from 11 to 15. So let's run this, and we do a select star from delta catalog blah blah blah, and let's run this. Okay, there you go. So you see that from 11 to 15 we have the payment method populated. That means that this statement worked pretty well, and automatic schema evolution had just happened. You didn't need to run an alter statement in order to make it happen. Now let's talk about the second scenario, which is type widening, right? And this was introduced in Delta version 3.2. This simply means that you can upgrade a type to its bigger type. Yeah, simply meaning that, let's say if you have an int, you want to convert it to a big int for whatever reason. The example that we discussed, if our orders have spanned to such a large number that it is not able to fit in the integer data type, we want to upgrade it to a big int, right? Similarly, you want to upgrade a float to a double, or a varchar of a specified number of characters to more number of characters. All of that is possible using type widening. So before we get started with example, we need to ensure that we at least have Delta version 3.2. And if you remember, during the initial parts of the video, I created a cluster. The cluster had a Databricks runtime version of 14.3. And I've pulled this up to show you that if I were to go to 14.3 and quickly search for Delta, this is going to be 3.1.0. That means this DBR, Databricks runtime, is not going to work. So let me quickly check 15.4, and what does that show me? So this shows me 3.2.0. That means this is going to work. So let me go ahead and upgrade this to 15.4, keeping all of the other stuff the same. Let's click on confirm and let's start the cluster. Okay, so now that we have our cluster ready, let's go ahead and start with the example. And before that, let me quickly write down scenario number 2, which is type widening. And we also need to do another thing, which is enabling type widening on this table. So let me how to enable type widening on a delta table. Let's quickly search for that. Okay, so this is the property that I need to enable, and let's go ahead and run this. Hopefully this should work. And meanwhile, let me go ahead and write an insert statement. Insert into this table. Actually, before that, let's see how the columns currently look like. So describe this table, delta catalog dot invoice delta db dot invoices se, right? How do the columns look like currently? So customer ID is an integer right now, and we have enabled automatic schema evolution, right? So let me go ahead and write an insert statement where values this. So I'll copy some values from here, and this is a string, this is also a string, comma comma, this is going to be a string, yeah, and this is an integer. So let me paste it over here, and I want to insert a number which is a big integer. Although you see that I have not currently changed the data type, but I still want to insert it and check whether it works or not, because I have automatic schema evolution enabled. So we want to try it out whether it works or not. So let's write, give me an example of a big int number, and that is the number that I'm going to use over here. So I have 6 columns, 6 numbers over here, and let's go ahead and run this. 36 values, not numbers. Okay, I missed a comma here. Let's run this now. Okay, so the error it throws is failed to assign a value big int to type int, right? That simply means that using automatic schema evolution, type widening won't work. We will have to manually change the type of customer ID. Yeah. So in order to do that, let's go ahead and run alter table invoices se, and we will write alter column customer ID, and the type that we want is big int. So let's go ahead and run this. That is successful. So we say describe table invoices se, and now you see that the customer ID is big int. Earlier it was integer. So let's go ahead and run the same statement again. Let's see what happens. Select star from. Okay, this seems to have succeeded. And if this actually succeeded, that means that this table should have a row where customer ID equals this value. Perfect. That means this row resides in the table and type widening has successfully worked, and we've enabled type widening. Next scenario that we are going to talk about is nested structure evolution. Scenario number 3 is nested structure evolution. So let's add a struct column to our table. So in order to do that, alter table, the invoices SC table, add column And let's go ahead and add something called purchase details, and this is going to be a struct. The struct is going to have two columns. The first one is mall pin code, the mall at which the purchase was made, and this is going to be an integer, and then the store code, the store at which the purchase was made. So let's go ahead and run this, and let's add some sample data to this table. So this is going to be, so we inserted around 15 records. So this is going to be the 16th one. So let's add 16th, and then we put a struct over here. The mall pin code, let's put in some random number, and let's put in some random number for the store code. Yeah, so let's go ahead and run this. So this should run just fine. So let's do select star from delta catalog blah blah blah, and perfect. So this should be the only row where you had purchase details, and it has all of the data that we just put in, the mall pin code and the store code. Now let's consider two examples. What if you need to change the data type of mall pin code for whatever reason from int to big int? And we're going to follow a pretty similar way. Alter table, this table, alter column, uh, purchase details dot mall pin code. The type that we want it to be is big int. Let's go ahead and run this, and let's insert some more data to validate this, and this is going to be number 17. Let's add in a struct over here, and the store code can be any number, but for the mall pin code I need a big int, so I'm going to put that number over here. Let's just increase it by 1, and this number can just be any other number, right? So let's go ahead and run this, and let's again do a select star from the table, and there you go. So this completely works fine. Now it is able to accommodate big integers, right? So that has completely worked fine. Now let's say if you want to add in additional attribute over here instead, apart from the mall pin code and the store code, you also want to add in the store location, right? So the way to do that again is very simple. We run this statement, and instead of alter column we just say add column, and let's say this is the store location, and this is going to be string, right? So let's run this. This works, and in order to test this out, let's run this statement again, and let me just put a simple number over here for now, and the store location is going to be the ground floor, for example. Yeah. So let's run this. Okay, I mistakenly inserted row number 17 again, but because we don't have any primary key constraint in place, this will work, but ideally don't do it. So let's now have a look at select star from this table, and we should see another row for 17, and this basically has the store code location equals null. The previous one, actually this is the recent one, so the store location is the ground floor, and you see that all the others have adjusted and the schema is maintained. The store location is null for all of the others, right? So this shows that schema evolution inside of the struct, inside of nested structures, also work pretty well. Let's understand automatic schema evolution inside of a nested structure with a few examples. And first let me ensure that that automatic schema evolution property is set to true, which is this one. So let me run this again, and what we want out of this example, right, what we want to understand out of this example is that initially if I wanted to add store location, I had to run an alter statement over here. So if I want to add an attribute to a struct, I need to run an alter statement. Now with schema evolution, the expectation is that if there is a new attribute coming in, so let's say apart from store location, there is a new attribute called staff ID. The person who helped make the purchase is coming in. I shouldn't have to run an alter statement. It should be automatically accommodated inside of purchase detail. So let's try that out. Let me copy this insert statement and let me paste it over here. This will be for, let's say, customer number 21, customer ID 21, and I will be using a named struct. The reason why we are using a named struct is because earlier, if you think of this, we already know that the first value over here is going to be mall pin code because it is there in the schema, right? 765 is going to be store code and ground floor is going to be the store location because all of this information resides inside of the schema. But now in this case, if we were to randomly insert a value over here, which is staff ID, I put in st some value over here, it wouldn't know what key does it belong to, right? So I need to specify the key so that it is able to add that key over here. Adding only a value wouldn't work, right? So I hope you understand why we need to use a name struct. So I'll simply add the keys over here, which is going to be mall pin code. This is going to be the store code. This is going to be the store location. And the last one is going to be the staff ID. Okay, so let's go ahead and run this. Perfect. So this seemed to work fine. Now let's quickly validate the data. And there you go. So you see that staff ID has been inserted correctly. And we didn't have to run an alter statement to accommodate this inside of purchase detail. And as we would expect, right? All of the other purchase details have staff ID equal to null. And this makes the whole schema very consistent. Let's finally understand the last scenario, which is column position changes. So I'll add in a header, which is scenario number 4, and this is to be column position changes. And first of all, I want to set this to false because I don't want to use automatic schema evolution for now. And let's go and do things manually first. So in order to add a column in a particular order, it is going to be add columns. And actually, let's figure out which column do we want to add first. Yeah. So we had these many columns and we don't have the age column yet in our table. So let me copy this statement because we are going to need this soon. So let me paste this here for now. Let's also see how our table currently looks like. Select star from the table, and we want to add the age column. Where do we want to add it? So there are two options. Either you can add it as the first column by specifying first, so this becomes the column before customer ID. The second option is you add it after some column. So let's say you add it after price. So then it is going to look like this. So let's say we want to run the second statement. Let's go ahead and run this. And now let's see how this is going to look like. There you go. You see age has found its position after price because that is what we ran. Now let's run an insert statement to see if all of this works or not. So again, I'm going to insert 5 records only to keep this simple. And the column that we have is customer ID, invoice number, price, and then we have age, then we have invoice date, then we have quantity, then we have payment method, and purchase detail was something that was added by us, so that doesn't reside in this Parquet file. So let me make it null for simplicity, null as purchase details. Do we have any other column? No. So let's run this. And now let's do okay, we'll just run this. So here you see that this has perfectly inserted the records from 50 to 55. All the columns have been populated correctly except the purchase detail column, which we purposely set it as null. That means column ordering has just worked fine. Let's see how column position change is going to work with automatic schema evolution, which simply means that if a new column comes in at whatever position, right, our table should be able to accommodate it. So let's say there is a new column called category which comes in, and I want it to be before payment method. It should be able to reflect that without me having to run an alter statement. Now again, I want to highlight that maybe this kind of a scenario we would never want it to be in production, right? Because we don't want some random data coming in and destroying our tables, right, destroying the structure of our table. But for the sake of completeness, I want you to know everything, like all possible scenarios, right? For now, let's insert category into our table. So let me copy this insert statement, and we are going to run this. And before this, let's also enable schema evolution. So schema evolution is being set to true, and let's also quickly print our table, right? So we see that we already have numbers from until 55. So this is going to be from 56 to 60, and the columns are customer ID, invoice number, price, age, invoice date, quantity, payment method, purchase details, and let me add category over here, right? So ideally category should just come before purchase details, if at all this works, right? So let's go ahead and run this, and this didn't work. The error says cannot resolve category due to data type mismatch. Okay, I don't want to correct then run this again. Data type mismatch cannot cast string to struct data type. So an important thing to understand here is that ideally this is the set of all of my columns, right? And this is an extra column that I just added. So if you were to just remove this for now, and if you were to think that this is your purchase detail, this is your purchase detail, then all of the columns should be completed with this, right? This would be an extra column. So what the insert statement is throwing as an error is that this category over here is supposed to be the last column, and the last column currently is a struct data type, but what you're giving me is a string data type, and for that reason I'm throwing an error. So that's the cause of this error. And now let's go ahead and try this with a merge statement. Let's see what happens with the merge statement. So we say merge into delta catalog. This is going to be the target using this table right here as the source on target dot customer ID equals source ID, source dot customer ID, where when not matched, then insert star, right? So here the code is exactly the same. Category is not in the correct position, and category is added as an extra column over here. So let's say what happened. Okay, that seemed to work, and we are going to run this. And okay, you don't see category column before purchase details, but you see the category column after purchase details, and this is quite interesting, right? So we read that merge does a matching by name. So it was able to match all of these columns, all of this over here, and purchase details by name. So it inserted them at the right places. The only thing that it was not able to match was category, and it inserted it as the last column. So the positioning didn't work, but you still ended up putting the data inside of the table, right? Now let me take you through how schema evolution is going to look like with Spark data frame. Yeah, and the way we are going to do that is by quickly taking some of the Parquet data that we read above, right? So I'm going to take this one, this Parquet files, and we are going to do a from PySpark.sql.function import star. Let's filter the customer ID dot between 1 comma 10, and let's also select a few columns, right? Customer ID, price, invoice, date. And let's go ahead and write this df.write.save as table. This is going to be in delta catalog dot delta db dot schema invoices schema evolution spark df, right? So let's go ahead and write this. Okay, this should be percent python, and if everything works, we should see a table here inside of our catalog, and there you go. So you have the table, we have the table that we created. Now let me add a few more column, right? So let me add quantity payment method, quantity and payment method. We added quantity and payment method, which changes the schema of the table, right? So I mean, we have not written it, but the schema is different from what we had over here. So let me choose customer IDs from 11 to 25, and let's write dot mode append dot option merge schema to true. Let's go ahead and run this now. And now let's see how our table looks like. Okay, so you see that from 11 to 25, we have the data for quantity and payment method, but from 1 to 10, we don't have data for quantity and payment method, right? And this is because the schema has evolved due to writing merge schema equals true. So now we are going to understand how to convert Parquet files into the Delta format. So most of the times your input files or your existing files are not going to be in the Delta format. But in order to be able to use the awesome features that we've been talking about, we need to convert it to Delta. Yeah, so that is what we are going to understand through a lot of examples. So I'm going to use the same Parquet file that I've used earlier. So I'll just copy the path of this Parquet file, and first of all, let's quickly do a %fsls and see what's there inside of the invoices folder. And we see that there are 3 Parquet files, and let me go ahead and use this one. The customer ID is from 1 to 100. So let me first create copies, 2 copies of this. I'm creating 2 copies because I want to show you 2 ways of converting from Parquet to Delta. So spark.read.parquet, and let me do a mode override dot Parquet, and let's paste the path. This is going to be, let's name it as v1, and let's not keep it in the invoices folder, and this is going to be v2. So basically where it is going to reside is inside of the lab data container at the root. Yeah, so here if I go back, So here is my lab data container and it is going to reside over here. Yeah, so let's go ahead and run this now. Now I should see two folders. So these are my two folders, right? So these are Parquet files, and if you see here, it has a .snappy.parquet, and this is where the data is stored, and it doesn't have a delta log folder. That means this is not a delta table yet. Same applies for this one as well. Yeah. So now let's go ahead and try to convert this to delta. So convert to delta, and then I write Parquet dot, let me paste the path. So now let's go ahead and run this. Okay, this is complete. So there you go. You see a delta log folder, which is going to record the transactions. And let's go ahead and see what's inside of JSON. And there is an add operation which added this Parquet file. So it registered this transaction, right? Now let's try another method. Let's say you want to use the delta table API, import delta table, and the method that we are going to use is convert to delta. We pass Spark over here, and this is going to be, the format is Parquet dot, we specify the tildes over here, and we copy this path v2 because we want to convert v2, and let's go ahead and run this. Okay, this is complete, and let's have a look at this now. So you see the delta log over here as well, and let's check this, and this should also have an add operation which registered the data, right? So this is how you're able to convert a Parquet file to a delta table, right? And similarly, you can do it for a CSV file or a JSON file or anything else, right? Maybe the approach would be a little different. You would have to read the CSV file into a data frame, something like df equals spark dot read dot CSV, and then maybe the path over here, and you have to write it. Let's say the mode is overwrite, and then the format is going to be delta, and then you specify the path over here, whatever path you want it to be, right? So this is another approach that you can follow in order to write your CSV or any other format of files. Now let's understand what are managed and external tables. Actually, the table that we've created in most of our examples, they are managed tables, but let's understand them in a lot more details now. So managed tables are those tables where your both your data and the metadata, they are managed by Delta Lake, right? They are managed by Delta Lake, and we create Delta Lake or Delta tables, right? We create Delta tables using the Unity catalog. Now, where does Unity catalog store data? Unity catalog stores data inside of a storage account inside of this container called metastore, right? So that is where it creates your tables. So the tables that we create, they are stored and managed inside of this container metastore, right? It's stored in a managed location. And in case of an external table, both the data, actually the data is stored in a user specified location. It can be an S3 bucket or an ADLS Gen 2 container or Google Cloud Storage, right? But the metadata resides in the metastore of the Unity catalog. And the metastore again could be something like this, right? So the metadata is going to reside in the metastore of the Unity catalog, and the data is going to reside in a location of user's choice. So now let's see this in action. Let's see an example. If I were to pull up any one of the tables that I created earlier, we see that, let's pick up invoices SE. Let's go to details, and what you see over here is the storage location, right? So the storage location is this storage account inside of this container. The container is called metastore, which is the one over here, and there we are going to have tables, and this is the unique identifier of my table. So my table is going to be this one, and all of the data and metadata is stored over here, is managed by the Unity catalog. That's one. Now let's try to create an external table. So let's write some SQL create or replace table, and this is going to be delta catalog dot delta db dot invoices underscore external. So I'm going to be using delta because the output, the underlying storage that I want, is supposed to be in a delta format, right? Now this can be any format, but I specifically want it to be in delta, so that is why I say using delta. And then I specify what is the location where I want to store my data. Let's go ahead and use this. Let's put it in some other location, this time not the meta store. Let's put it inside lab data. So I have lab data over here, and let me name this as invoices external, and this is going to be as select star from Parquet dot, let's say this file over here, right? So let me paste this over here, and let's run this now. So let's see if this table exists in the catalog. So there is a table invoices external, and let's see the details. Now the storage location is not in the meta store. It is the location that we specified, right? So let's refresh this, and this is invoice ext, and you have this as a delta table, right? Now the second difference is if I do a drop on a managed table, the data, the underlying data, is going to vanish, it is going to go away. But in case of an external table, this data that you see over here, even if I do a drop on this table, right? So if I do something like a drop table, the underlying data is still going to stay in the user specified location, right? So let me go ahead and run this. Now this should disappear from the catalog. It has disappeared indeed, and let me go ahead and refresh this. So you see that the data is still there in the user specified location. And if this were a managed table, the data would have gone. So actually sometimes in cases of managed table, you would still see the data because of a default retention period. Sometimes the retention period is set to 30 days. So that is the reason why the data doesn't disappear immediately. Now the third point of difference is that managed tables use the delta format only. So all of the tables that are created in the Unity catalog residing inside of this meta store follow the delta format only. The managed tables follow the delta format only. But in case of external table, they could follow several formats. It can be CSV, it can be JSON, it can be a Parquet, right? It can even be delta. So in the last example, we saw that we've written using delta. And because we wrote using delta, it created the output in a delta format, right? If we wrote using Parquet, it would create the output in a Parquet file format, right? So that's the reason why several formats are supported for external tables. So now let's talk about something really interesting in Delta Lake called deletion vectors. And I believe we've already seen it in action, but now let's talk about it in a lot more detail. So first of all, let's understand what is the problem, what is the issue at hand that deletion vectors is trying to solve, right? So we already know that delta uses Parquet files under the hood for storing its data, right? And Parquet files are immutable. So what I mean by immutable is that they cannot be modified directly, right? So if you want to update or delete a record in a Parquet file, what you essentially need to do is you read the Parquet file and then you apply those operations, delete or an update, and then you write the Parquet file back, right? So that is the only way you can update or make changes to that file, right? You read it, apply the operations, and then write it back. Now this rewrite process, this whole read and rewrite process is very costly. Imagine if you had a Parquet file with 10 million rows and you only needed to delete a few couple of rows, right? So what you would end up doing is you would read the whole Parquet file and you would rewrite the whole Parquet file again, except for those couple of records which you want to delete. Yeah. So this is a tremendously computationally expensive operation, and this is where deletion vectors come into play. Now before we talk about deletion vectors, let's talk about two important concepts. The first one is copy on write and the second one is merge on read. Yeah, so let's understand copy on write first. Copy on write is exactly the same as what we discussed above, right? Every change, every update, every delete or a merge is going to create a new file, right? And delta is going to follow this approach when deletion vectors are disabled. So it's very important to keep in mind that copy on write is going to be followed when deletion vectors are disabled. Yeah. So let's take this example. Let's say we have a Parquet file, one.parquet, and it contains 1,000 records, right? It contains 1,000 records, and that is what we see over here from 1 until 1,000. And now what we want to do is we just want to delete rows number 1 and 6. So the most simple way that copy on write is going to do is that take up this whole Parquet file, right? You take up this whole Parquet file and then apply the delete operation. You apply the delete operation and then you rewrite the whole file back except rows number 1 and rows number 6. So these two rows are going to be omitted and then the whole file is going to be written back as you see over here. So it doesn't have rows number 1 and rows number 6 over here, right? So the new state that you see is that a new file which is 2.parquet is written to storage, right? And this file is going to be the one to be referenced for the latest version. So that is how copy on write works. Now, in contrast, what merge on read does is that it allows your original Parquet files to remain untouched. And instead, the changes that we apply, right? For example, deletions, they are recorded in a separate file known as a deletion vector. Yeah. So let's say if I want to delete a record, that row number is recorded in a deletion vector. And when I read the file, the deletion vector is simply going to be checked if this row is present in the deletion vector or not. If it is, then that row is going to be skipped from the output. Yeah. So delta is going to follow the merge on read approach if deletion vectors are enabled. Yeah. So it's really important to keep this in mind again. If deletion vectors are enabled, merge on read is going to be followed. If not, copy on write is going to be followed. So now let's understand this with an example. Yeah. So let's say we have the same Parquet file with 1,000 records. Yeah. So 1,000 records as you see over here from 1 until 1,000 over here. And we want to perform the same operation. We want to delete rows number 1 and 6. Yeah. So this time what happens is when we say we want to perform a delete of row number 1, which is right over here, we simply record it in a deletion vector, which is over here, right? The next time we say that, okay, we want to delete row number 6, what happens is we record row number 6 in the deletion vector again, right? So all of these changes are getting recorded in the deletion vector. and all of this data that you have over here, they are stored in one.parquet. So now let's say I want to read the file, right? I want to read the latest state. So when I read the latest state, I would expect that row number 1 and row number 6 shouldn't be there in the file, right? So the way I'm going to get the output is that this whole file is going to be produced as output, and this row is going to be checked against the deletion vector, that is it present in the deletion vector or not. If it is, then this is marked as a soft delete and you won't see that row. So this won't be produced in the output. Similarly, this row is going to be checked. Is it present in the deletion vector or not? It's not present. So that means this row is going to be displayed. Similarly for all the rows. And row 6 would also be checked and it would not be displayed, right? So that is how it helps you in not rewriting the entire file back. The final state that you would have is one.parquet, the whole file is untouched, and a small deletion vector bitmap file, right? Where all of the deletes, all of the changes are getting recorded and it is going to be checked against. And this is going to add a lot of speed to the entire process, and it is going to make a lot of things more performant. So we see that deletion vectors bring the merge on read capability to Delta Lake, thereby increasing the performance of deletes, updates. So update is considered as an insert plus delete, and merge operations, right? So instead of rewriting the whole file back for small changes, what it does is that it records those small changes in a separate bitmap file known as deletion vectors. Let's see all of this in action now. Let's get started with our labs. So I'm going to quickly pick up one of the old Parquet file that we've been using, and let me quickly do a select star from Parquet, and then this one. Let me use the 20101 to 201, right? And let's keep the default as SQL because we're going to write lots of SQL. Let's connect this cluster and let me quickly do a limit 5 and let's go ahead and run this. Meanwhile, first we are going to explore copy on write. So let me quickly write how to create a table with deletion vector disabled, right? So let's see how this works. Great. So let me do create or replace table, and the catalog that we're using is this one, delta catalog dot delta db, right? So this is going to be delta catalog dot delta db dot invoices, and this is going to be COW, copy on write, right? Yeah. And let me quickly copy this over here in the table properties, delta dot enable deletion vector to be false, and this is going to be created as a CTAS, creatable as select statement. So let's go ahead and run this now. Yeah. Let me also write a describe extended and then delta catalog dot delta db dot invoices. Yeah, so let's run this and have a look at some of the properties quickly. So here we see that this is a managed table and the deletion vector is not enabled. Yeah, let's also see where does this table reside inside of ADLS. So let me quickly open up ADLS. And this is the table right here. So it basically contains one Parquet file at this moment, right? Now let's go ahead and perform some operation, right? So let's say this user 105 from age 57, let's say it was incorrectly recorded and we want to correct the age to 55 for user 105. So we are simply going to say update this table set age equals 55 where customer ID equals 105, right? So this customer is 105 right here. So let's go ahead and run this. And let's also see the history. Describe history and this table. So it should contain two rows. The first one for the create. Yeah, the first one for the create and the second one for the update, right? So based on whatever we've studied and understood right now, this update should create a fresh Parquet file, right? With the changes. So let's go ahead and understand a few metrics, the operation metrics over here, right? So what it says is that number of removed files equals 1, number of copied rows equals 99. So we see that we had a total of 100 rows over here, right? From here. And the row that got updated is just one row, which is row number 105. So other than that, it copied all of the 99 rows. No deletion vectors added or removed because deletion vectors are disabled. Number of added files, so it added a new file, right? And then it updated one row, quite similar to what we would expect, right? Because we ran an update statement over here. Now let's go ahead and see how this would look in the storage. So we see that this has added another file, it has rewritten another file, yeah? And if you were to quickly look at the sizes is more or less the same, right? This is 5921 and this is also 5921. Yeah. Now let's go ahead and run another statement. This time let's go ahead and run a delete statement. So let's go ahead and delete the row for customer ID equals 102. So I'm going to write delete from this table where customer ID equals 102, right? So let's go ahead and run this. And let me also see what the history is going to show me. Now we have three rows, the third one for the delete operation, and let's quickly see the operation metrics. So now the operation metrics, what it says is number of copied rows is 99, number of deleted rows is 1. Yeah. And then it added all of this in a new file, right? It basically removed the file that it read in the previous version. That is why you see number of removed files 1, and then it added this new file. It deleted one row over here because number of deleted rows equals 1. And let's have a look at the size. So this is 5897 and this was 5921. A little smaller because we deleted one record. Now if we have a look over here, we should see one file over here. Yeah. There you go. So we see this file which was added at 1639. This file was added with 99 records. Yeah. So I believe this confirms how copy on write works. It is reading the file, applying the changes, and then writing it as a new file. So let's now see how is a delta table going to behave if merge on read was enabled. Yeah. So we've already discussed that if deletion vectors are enabled, then the paradigm that is going to be followed is merge on read. So let me create this table and I will rename this to MOR and let's set this to true, which is going to enable deletion vectors. And let's go ahead and run this. I will do a describe extended this table just to verify a few of the properties. So this is a managed table and delta dot enable deletion vectors is set to true. Now let's go ahead and perform similar operations that we performed on the earlier table, right? The table where deletion vectors was disabled. So let's go ahead and run this, and this is going to be MOR, and I'm going to do a describe history of this table, and I should see two rows. Yeah, the first one for the CTAS and the second one for delete. So let's understand a few operation metrics, right? So what it says is that number of removed files and the number of removed bytes is 0. And this is a little different from what we saw earlier. What we saw earlier was it removed the file and then it performed the delete operation and then it wrote the file back. Yeah. But here what we see is a little different. There were no files that were removed and there were no rows that were copied. Instead, there is a deletion vector that has been added. Yeah. And the number of deleted rows is 1, which is exactly what we did over here. Yeah. So that's all of the operation metrics, right? Now let's quickly see how does it look like in the storage, in our storage layer. Yeah. So let me copy the file identifier, and this file is right here, and there you see that this is the original file. We don't have another new file as you would see in a copy on write paradigm. We only have the old file, and then we have a deletion vector which records the rows which we need to delete. Yeah, very simple and very performant because it didn't have to rewrite the whole file. Now let's go ahead and perform another operation, which is the update. So I'll just change the name of the table and the operation will be just the same. And let me do a describe history as table, and I should see 3 rows. Yeah, the third one is an update. And let's quickly have a look over here. So the number of removed files is 0, number of removed bytes, number of copied rows is all 0. What it did is it added a deletion vector. Yeah, it removed the old deletion vector and then it added a new deletion vector, right? So the new deletion vector has been updated with more details, and that is what we would see over here. So if I were to look at, quickly refresh this, what should we expect? So we should expect two things. The first one is that I should expect a Parquet file, because as we've read in the earlier section, an update is considered as a delete plus insert. Where is the delete going to be recorded? The delete is going to be recorded in the updated deletion vector. So one more deletion vector should be created, and the row that is updated, that should be recorded in another Parquet file. Yeah, so I should see one more Parquet file and I should see an updated deletion vector, that is one more deletion vector. So let's refresh this, and there you go. So you see one more Parquet file and you see one more deletion vector, and this is the updated deletion vector. So now you may have this question that on a table there could be several deletes, updates and merge operation that could be going on, right? And as a result of this, as you see over here, it could generate a lot of small files, a lot of deletion vectors, right? So what is the way to clean this up, right? To tidy this up, because there are two deletion vectors over here. One is obsolete, the other one is updated, and then there is this one file over here which just contains one row, right? So for all of this, Databricks provides us the optimize command. So you have the optimize command that you can apply on a delta table. So let me go ahead and quickly show you. So let's say we run the optimize on this table, and what it does is that it is going to create a new version, and that new version is going to be the latest state with all of the deletion vector and all of those computations applied, right? So it is going to check which row it's supposed to be there in the latest version, do all of those computations and then create one fresh Parquet file, right? So over here, I should just see one fresh Parquet file created using all of this, right? It is going to apply all of the computation, deductions, and then create one new Parquet file. So now what we see over here is that this new Parquet file has been added, and this has been created by computing the latest state. Now if I were to do a vacuum, yeah, so vacuum basically keeps the latest state. It is going to remove all of the history. It is only going to keep this final file, right? Because this final file contains the latest state. So let's go ahead and run vacuum this table and then retain 0 hours, and then we also need to set a configuration which is called set spark.delta spark.databricks.delta.retention duration check.enable is false, and let me go ahead and run this. So it is going to clean up all of the older versions, and what we should end up seeing is just one Parquet file, which is the one created at 1814. Yeah. So let me refresh this, and there you go. So you see that the file that was created at 1814 was the latest file, right? And this has been retained when we run the vacuum command. So by now we've seen deletion vectors, copy on write, merge on read, all of it in action. Yeah. So it's really important to understand that neither paradigm, neither copy on write nor merge on read, offer a silver bullet for all use cases. Yeah. However, copy on write is really good for use cases which is read heavy. Yeah. And where the writes are very low. What will happen if the writes are high? It will simply read and rewrite the whole file again and again and again, right? And we want to avoid doing that because it's a costly operation. Yeah. So copy on write is good for read heavy use cases, and similarly merge on read works best for use cases where data is updated frequently, right? Why does it work best for use cases where there are frequent updates? That is because it is simply going to record those changes in a deletion vector file. It is not going to rewrite the whole file. So ultimately, it helps you reduce the write latency because it is simply recording it in a deletion vector. Yeah. So I hope that helps you understand the trade-offs between the two and how deletion vectors can help boost performance. So now we are going to talk about cloning. So cloning, as you know, lets us create a snapshot of our delta tables at a specific point in time, right? And there are two flavors to cloning. There are two approaches to clone a delta table. The first one is a shallow clone, and the second one is a deep clone. So let's understand both of them in details. Shallow clone is essentially taking the snapshot of metadata at a particular point in time, right? So when you shallow clone a table, Delta doesn't copy the underlying data files, right? It simply references them. So let's say there is a source table and then there is a shallow clone table. The shallow clone table is simply going to reference the Parquet or the underlying data files, right? It is not going to copy those data files. So what this means is that it makes the shallow clone operation super fast, computationally cheap, and it doesn't eat up a lot of storage. So let's understand this with this diagram right here. Let's say we have a source delta table and we want to shallow clone this source delta table into a target table. So what the source table has is this metadata over here in the delta log folder, and this is some bunch of JSON files that you see over here, right? And then it also has some data in the form of Parquet file. Yeah. So now if we want to shallow clone, this table, the first thing that is going to happen is a duplication or a replication of the metadata itself, the metadata that we have over here. And when I say duplication, what I mean to say is that it's not a one-to-one copy of these JSON files, right? It's not that I'm going to copy 0.json, 1.json, and then put it over there, right? Put it in the source, in the target table, right? So that's not the purpose. What is going to happen is that all of this is going to be condensed into a checkpoint.parquet file, and then the latest state of this source table is going to be computed, and that is going to be put in 0.json. So you would see that these two files would be present in the delta log folder, in the delta log folder of the target delta table, right? So this one is going to be used in order to compact all of the information that you have over here, and we put it into a 0.checkpoint.parquet, and the later state of the source table is computed, and that is put inside 0.json, which becomes version number 0 of the target table. So the target table is going to start with a fresh version, which is version number 0, right? And what happens to the data? So the Parquet file that I've shown over here, it doesn't actually mean that there are going to be Parquet files, right? It is just symbolic of the fact that there is going to be data in this target table, and this data is going to reference all of the Parquet files that you see over here, right? So it is simply going to reference all of the Parquet files that you see in the source table. And that is how a shallow clone works under the hood. Now let's understand what deep clone is, right? So a deep clone makes an independent copy of both the metadata and the data files, right? So this operation takes a little bit longer. It uses more storage because now this time it is not referencing the data of the source file, right? It is actually copying the data of the source file in the deep clone file in the target, right? So this is going to use more storage, but the result is that it is a completely self-contained and an independent table, right? So let's understand that with this diagram right here. And again, we have a source table and we have a target table, and we want to deep clone the source into the target, right? We want to deep clone the source into the target. And similar to the last example, we have metadata in the delta log folder with a bunch of JSON files that you see over here, and some data files, and these data files are basically Parquet, right? Now when we do a deep clone, the exact same thing is going to happen for the metadata. All of this is going to be condensed into a 0.checkpoint.parquet, and the latest state is going to be computed, put inside 0.json, which is going to be version number 0, right? Which is going to be version number 0. So the deep clone table is going to start at a fresh version, which is version number 0, right? And as you see over here, all of these Parquet files, right? This one, this one, this one, and this one, this one, and this one, and this one, and this one, they are going to be exactly replicated, right? So this is going to be exactly replicated. So this is going to be a one-to-one copy. So that is how a deep clone is going to work under the hood. Now let's see all of this in action, right? So first of all, we are going to start with shallow clones. We're going to start with shallow clones, and for this purpose, I am going to create a new table with customer IDs from 1 to 100, and I'm going to use a CTAS statement. I'm going to use a CTAS statement. So this is simply going to be create or replace delta catalog dot delta db dot invoices of customers from 1 until 100, right? Because that is what we are doing over here. And let me just put as, and this is going to be create or replace table, and let's go ahead and run this. Let's also quickly do a select star just to see how this looks like, right? Select star from this table, limit 5. Yeah. Okay, so this looks fine. Now, if I were to do a describe history of this table, delta catalog dot delta db dot invoices underscore c 1 to 100, we are simply going to have one row. That is the CTAS statement that we ran, right? So now, in order to add more history to this table, let's perform a few more operations. Yeah. So let me go ahead and do a delete from this table where customer ID is between 15 and 20. Yeah. Let's run this. Let's run another statement, which is an update this table where, so what do we want to update? So let's update customer ID equals 3 and let's change the quantity from 3 to 10, right? So this is going to be where customer ID equals 3 and I need to set this quantity to 10. Yeah. So let's run this again and let's also quickly see how the layout looks like in the file storage, right? So if we go to details and this is the storage right here. Okay, so here you see two files and then two deletion vectors, right? So I believe the first file is for the first instance when we did a creation using the CTAS command, right? The deletion vector, the first deletion vector is for the delete command, and the file, the Parquet file and the updated deletion vector that we see, actually this is the updated deletion vector because this is created at 1739. So the updated deletion vector that we see is because of the update command, and the updated row is contained within this Parquet file. Now let's go ahead and run an insert statement. So insert into this table, and then the values, let me quickly copy from this table right here, right? So this is, let me put a random customer ID which is 1099 and let's quickly format this. Okay, now that this is formatted, let's go ahead and run this. Okay, so the insert statement is complete, and if I were to go to the file storage ADLS, we should see another Parquet file over here that is going to contain that insert statement, right? There you go. So we see another Parquet file over here, right? The one that ends with 12CB-C000, right? So now let's do a describe history of this table. We should see 4 rows. Yeah. So the first one is for the CTAS. The second one is for the delete between 15 to 20. The third one is the update where we updated customer ID equal 3, and the last one is the insert over here, right? So all of this makes sense now. Now let's say we want to do a shallow clone of this table. Let's see what is going to happen. So first of all, let's write a create or replace table, and this is going to be the same, and I'll just append it with HCL shallow clone, and let's write shallow clone and the table over here, delta catalog with this, right? So let's go ahead and run this now. Let's see what happens. Okay, so if I were to look at the catalog, this should show me this table. So this table is created right here, and if I were to look at the details, I would find the path, and let's have a look at what is there in this path. So let me just open this in a new tab. So now the interesting thing is you only see the delta log, right? So we were talking about that the files are referenced. So that is why you don't see any file over here. And let's also see what there in the delta log. So as we discussed, we see a 0.checkpoint.parquet and the latest state in 0.json. So I hope all of that makes sense now. You're able to connect the dots. Let's look at a few more details of the shallow clone table. So if I were to say describe history of the shallow clone table, I should essentially see one command, yeah, which is the clone operation itself. Now, if you look at the operation parameters, it tells me that the source of the table is this table over here, right? And the source version, right? The source version, the latest version of the source table was number 3, and that version was used to build the shallow clone, right? So that is what it says over here. Source version is number 3 and is shallow equals true. Yeah. Now let's update something in the source table and see if it affects the shallow clone table, right? So we have the source table right here, uh, over here, right? So let me do a quickly do a select star from this table. Select start from this table and let me do a limit 5 and let's go ahead and run this. So I want to update some row. So let me update customer ID equals 5 this time. So customer ID equals 5 has quantity equals 1, but now I want to update it to 10. So let's go ahead and run this. Let's also see the history of this table. So now it should contain an update, right? So after an insert that we did previously, it now has an update. So let's quickly do a select star from this table where customer ID equals 5, and now I should see quantity equals 10, right? I see quantity equals 10. Let's quickly verify what is the resulting value in the shallow clone table. So we see here that quantity equals 1 and customer ID equals 5. That means even though the shallow clone is referencing the source table, after the point that the shallow clone has been cloned, right? The target shallow clone table has been cloned, it is going to have its own history, its own set of operations, and any activity on the source table is not going to affect the shallow clone, right? I hope this is very clear. Now let's try something different. Let's try deleting or modifying some records in the shallow clone table, and let's see whether that affects the source table or not, right? So let's do a delete from delta catalog dot delta db dot this table shallow clone where customer id equals 99, right? So let's go ahead and run this, and let's also quickly run select star from this table where customer id equals 99. So this shouldn't return me any row. And let's also have a look at the history. Okay, so no rows returned. Let's also have a look at the history of this table, and it has a clone and then a delete, the delete operation that we ran just now. Now if I were to compare this to the original table, ideally I should find the record, right? Because the operation that a shallow clone is going to have is going to maintain its own history after the point it has been cloned. So any operation on the shallow clone table shouldn't affect the source table. Yeah. So let's go ahead and run this. And there you go. We find that the row number 99, customer ID equals 99, is still there. And let's also verify this with the history just to make sure that the history also remains unaffected, right? So let's run this, and there is no trace of a delete statement, right? So after the shallow clone table is cloned, it maintains its own history, right? So now to quickly summarize, once a source table has been shallow cloned, changes or updates or modifications or deletes to the shallow clone table is not going to affect the source table, and changes or updates or modifications to the source table is not going to affect the shallow clone table, right? The shallow clone table is only going to refer to the data of the source table until the point the clone happened, right? From that point onwards, it is going to maintain its own version, its own history, its own data files, right? So I hope that makes sense. Now what I want to show you is that we can also clone a table using a particular timestamp or a particular version number. Yeah. So what we can do is that we can run a create or replace table, and this is going to be shallow clone. Let's create a clone of version number, this version, right? Version number 0, v0, and this is going to be shallow clone delta catalog dot this table version as of 0, right? So let's run this now. So if this has worked properly, you should not see, actually you should see records from customer IDs 15 to 20, right? So let's start from this table where customer ID between 15 and 20. Now if I were to similarly run this on the original table, I shouldn't get any records, right? Because the latest version of this table doesn't have those rows from 15 to 20. Yeah. So let's run this. And there you see 15 to 20, but in the original table, there should be no rows returned. Okay, that works. And another variation of this is that you can also do a timestamp as of, and you can basically pick up any timestamp over here, right? So you can pick this one up and write something like this, right? Now let's talk about time travel. So if I were to quickly show you, okay, let me just note this down. Time travel. If I were to show you describe history of this table, we are going to have several rows, right? Because we performed several operations. Now, what I've already mentioned earlier is that when we create a shallow clone, it starts from version 0. It takes up the latest state of the source table and it starts from version 0. So if I were to do something like this, create or replace table, and let me put this as test shallow clone, as shallow clone this whole table, right? So if I were to run this, as we've already seen earlier, this is going to create this table taking the latest version of this table over here, right? So if you do a history on this table, it is only going to contain one row, right? So I'm reiterating all of this, right? Because I want to make sure that this is super clear. So you see that there is only one row. That means version number 0 of this table has been created using the latest state of the source table. So the source table has many versions, right? It has version 0, 1 until 4. If I want to roll back to a particular version, or if I want to see a particular version of the source table, I can definitely do that, right? I can see version number 3, version number 2, version number 1, and so on. But just because we have shallow cloned this table, it doesn't mean that we can access the history of the source table. We cannot go back to version 1 or 2 for this shallow clone table, right? So I hope that is clear, because we are going to start with a fresh history, with a fresh version, with version number 0, taking the latest state of the source table. Now let's try out something interesting. Let's run a vacuum on the source table, and by source what I mean is this table right here, invoices underscore c1 underscore 100, right? So if you remember, when we created this table, right over here, we ran a few statements in order to populate the history. The first one was a delete, the second one was an update, and the third one was an insert. And I also pointed out that this is the Parquet file where the value of that insert was stored, right? So the customer ID that is belonging to this insert is 1099, and this table later on was cloned, right? So that means that this row where customer ID equals 1099 is present in the source table. It is also present in the shallow clone table, right? So the shallow clone table is also referencing this row. Now, if what happens if I were to run a delete? So let me just quickly add this heading, and let's say I run a delete from this table, where customer ID equals 1099, and this should ideally remove this row, right? So like start from this table where customer ID equals 1099, right? So this should not give me any result. Okay, that works perfectly fine. Now, because this file is now orphaned, right? This file is not being referred in the latest version. When I run a vacuum, this file should just go away, right? That is how vacuum is going to behave. So first of all, I have to set this property, set spark dot databricks dot delta dot retention duration enabled is false, and then let's go ahead and run a vacuum this table retain 0 hours, right? Let me go ahead and run this, and ideally if everything works out fine, I shouldn't see this Parquet file which ends with 12cb-c000, right? So let me go ahead and run this. Okay, this is complete, and let me refresh this. Okay, so one of the deletion vectors was cleared, which is good, but I don't see the file deleted, right? The one ending with 12cb-c000 is not deleted. Why that may be the case, right? So can you think of why this may have happened? So the reason this has happened is because although this file in the source has been deleted, there is a shallow clone which is still referencing that row, right? So that is why that file has not been deleted. So let me show you. If I were to run this on the shallow clone table, this is there, right? Now let me go ahead and delete this from all of the shallow clones that I've created. So by now you must have seen that I created a few shallow clones, and we want to remove all of the references of that row 1099, right? So this would be delete from delta catalog dot this table where customer ID equals 1099. What were the other tables that I created? It was v0, and what else? So I created v0 and then underscore test underscore scl underscore test underscore scl. So I want to remove all of the references, right? So now what this means is that this was the source table and there were several shallow clones. Some of them were referring to row number 1099. Now I have removed all of the references. So that file is now an orphaned file. There is no reference. So once I run a vacuum, that file should be gone now, right? So now let's go ahead and run this vacuum once again. Okay, so this is complete now. So I believe this file should be gone if whatever logic that we were discussing is true, right? So let's refresh, and there you see. So you have only 3 files and that file is gone because there are no more references to that Parquet file anymore, right? Now let's see deep clone in action. So let me quickly put that down as a heading, and I want to clone the source table that we've been using so far, which is this one. So let me quickly see the history. Okay, so there's a lot of things that we've performed on this table, right? And let me also see how the file looks like, right? So this is how the files look like, right? Now let me go ahead and
perform a deep clone, create or replace table, this table, and this is going to be a deep clone. Let me also remove this, and let me write this as DCL, which is deep clone, right? So let's go ahead and run this. Okay, so this has created a deep cloned table. Let's see, describe history of this table, and ideally we should just see one row, which is the clone. Perfect. And if we look at the parameters, we see that this is being cloned from this table and the source version is 13, right? 13, the latest version. Yeah. So let's have a look at a few other things. So if I were to check how the files look like, right? So let me have a look at how the files look like. So what you see over here is that these two are an almost an exact copy. So there are three Parquet files and one deletion vector, and that is what you see over here exactly. So these are three Parquet files and one deletion vector, and this is a one-to-one copy, right? So we see, let's quickly check the numbers. So this is 967 F2B and 3D2, right? So this is 967 F2B and 3D2, right? And the deletion vector ends with 9F9. It also ends with 9F9, right? So that means that this is an exact copy from the source. But for the delta log, we discussed that there is going to be a 0.checkpoint.parquet and then 0.json, which is going to generate the latest state. And exactly that is what we see over here. Yeah. So now let's do a few other things. Let's make some changes in the deep clone and see if it affects the source table. Ideally it shouldn't, because we mentioned earlier that the deep clone is an independent and a self-contained copy, right? So let's make a few changes now. First of all, let me do select star from this table right here, and let's do a limit 5. So let's run this. So I'm going to write an update from, update this table, where I'm going to set the quantity of customer ID equals 4. I'm going to set the quantity to 10, where customer ID equals 4. And let's go ahead and run this. So let's quickly verify this from this table where customer ID equals 4. This should now be 10 instead of 5, and that is what we see over here. Now let me quickly verify this in the original table. The original table still shows 5, right? So as we expected, that any change in the cloned table, in the deep clone table, is not going to affect anything in the source table, and vice versa is going to be true. Any changes in the source table is not going to affect the deep cloned table, right? Now, I'm not going to run and show you a vacuum on a deep clone, because as I mentioned earlier, a deep clone is a self-contained and an independent copy, right, of the source table. There are no references between the deep clone and the source table. So if we were to quickly summarize what happened in the shallow clone vacuum, so we had a file, right? We had a file where customer ID equals 1099, and there were several shallow clones referring to that row. Now, when we performed a delete and then we did a vacuum, still that file was not removed from the source table. Why? Because shallow clone, there were three shallow clones which were referring to customer ID equals 1099. Once all of those references were gone, right? Once we deleted all of the references, we ran a delete statement, which meant that that row is no longer in the shallow clone. Those references were deleted, and then we ran a vacuum on the source table, we saw that the Parquet file was deleted, right? But in case of a deep clone, the source table and the deep clone are completely different. Different in the sense that they are independent copies of each other. There is no reference from the deep clone to the source table, right? So that is the reason why vacuums should be completely independent, right? So before we conclude this section on deep and shallow clones, I believe that a good number of you would have this question, that how are CTAS different from deep clone? So the tables that are generated using CTAS, create or replace table and then a select query, how is that different from the tables that are generated using deep clone? So if you were to look at it at an output level, so let's say you're doing a select star from whatever table, right? If you were to look at the outputs that are being generated by the two tables, one which is generated using CTAS and the other one that is generated using deep clone, they would look exactly identical, right? But that is not where the difference lies. So when you deep clone a table, you also clone, you don't need to re-specify the partitioning properties, the constraints, and all of that, right? With CTAS, the table is just created using the output of a select query, right? So you write a select and then it generates a set of rows and it just uses those rows to create a table. All of the properties are lost. And that is where deep clone comes in handy. It's a robust way to clone the metadata, the data, and the properties of the table. Another very important advantage is that it works in an incremental manner. So what I mean is that, let me show that to you with an example. So let's say we have a disaster recovery use case, right? So let's say we have a disaster recovery use case, and by this what I mean is that, let's say we have a source table over here, we have a source, and then what I'm doing is that I am having a replica. So this is the replica, and I am syncing these two tables, right? So what I did first is that I did a deep clone. I did a deep clone of the source table, right? Now what happens when I'm going to get an update? So let's say there is an update on the source table, right? And then there was a delete on this source table. What is going to happen? So I would need to bring these two tables again back in sync, right? So in order to bring this back in sync again, I would need to do a deep clone again, right? So I would end up doing a deep clone again. But the beauty of this is that it doesn't copy the whole source into the whole replica, right? It doesn't copy the whole thing again, right? It only copies incremental changes. So what it is going to do is that it is going to take this update and apply it on the replica. It is going to take this delete and apply this on the replica, right? So the whole table is not going to be copied again and again. The operations are copied or synced in an incremental manner, and that is the reason why deep clones are robust and they are very performant. So now we are going to talk about something that silently kills your Spark performance, and that is the small file problem. Yep, the small file problem. And we are going to understand what exactly the small file problem is, why does it happen, and how this can be fixed using Delta Lake's optimize command. Yeah. So let's first understand what the small file problem is and why exactly is it problematic. Yeah. So now I'm going to take a weird example, but it is just to help you get the right understanding. Yeah. So imagine you are reading a PDF. So imagine you're reading a PDF of a 300 page novel, right? So naturally, you would expect the novel to be a single 300 page PDF, isn't it? So you would expect it to be a single 300 page PDF, right? But what if
what if I would say that someone saved each of these pages as a PDF?
So what they did was they saved one.pdf, 2.pdf, until all the way until 300.pdf. So what they did is that they took each of those pages, each of those 300 pages, and saved it as a PDF. So how would you read this kind of a book, right? So first of all, you would end up saying some very nice words to that person who did this, which I cannot say on this video. But then what you would essentially do is that you would open the first PDF. Actually, you would look for the first PDF, right? So first of all, you would look for the first PDF, look or find the first PDF, right? And then you would open the first PDF and you would read it. And finally, when the reading is complete, you would close the PDF, right? Now you would have to do this for all of the 300 pages that have been given to you. And what we see here is that we've spent a good amount of time, first of all, finding the right file, and then opening it, and then finally closing it, right? So there is a good amount of time that you spend in all of these problems, in all of these operations, right? And that is exactly what the small file problem is. When you have a small file problem, there are too many small files, and then you end up doing such operations, right? You end up, first of all, finding the right file, and then opening it and closing it, right? And these are time consuming operations. So to reiterate, when you're reading a table and instead of having a few neatly packed files, if your data is scattered over thousands of smaller files, there is going to be thousands of those open, close, and metadata lookup or finding operation that we just discussed. All of this leading to wasted compute and poor IO, right? So all of these operations is simply going to lead to wasted compute and poor IO, right? So how does Delta solve this problem? Delta provides a built-in operation which is called optimize, and what it simply does is that it compacts all of these small files into larger, more appropriately sized one, right? And in order to do this, it simply uses something called a bin packing algorithm. It uses a bin packing algorithm, right? So we are going to see this in detail, so don't worry about it. Nevertheless, it's actually a very simple algorithm. What it does is that it collects all your file sizes and then it sorts it from high to low. And then it starts picking each file and it places each of these files in a particular bin. And think of this bin as one large file, right? So you have lot of small files over here, right? You have lot of small files. What it does is that it simply takes this and it puts them in a bigger bin as long as it fits in the bin, right? So let's say this simply is able to fit in this bin, this is also able to fit in this bin, this is also able to fit in this bin, but this one is not able to fit in this bin, right? So in that case, a new bin is going to be created and then this is going to go over here, right? So that is how simply the bin packing algorithm works, and I'm going to show you a visualization in order to help you to understand this better. But before we go there, I want you to understand that the default bin size that Delta targets is 1 GB, right? So this is going to be 1 GB. That is what is the default for Delta Lake, right? And this default 1 GB size has been selected after years of usage and testing on different kind of Spark workloads, and it's really proven to be robust, right? So this number 1 GB has really proven to be robust. So unless you have a very good reason to change it, don't change it. Go ahead and use the default 1 GB number. Yeah. So just to let you know, just in case you want to change it, there is a property which is called spark.databricks dot delta dot optimize dot max file size. So look it up on the internet, dot max file size. So you can use this property to change the 1 GB default number, but my advice is, again, don't change it unless you have a very compelling reason to do so. Yeah, so now let's see the visualization. So here we have a list of files, a list of Parquet files, and it has simply been sorted in descending order by file sizes, right? So the first one you see is 320 MB and the last one is 80 MB. So we are going to run through how bins are going to be created, right? And again, we are assuming that the target size of one bin, one file, one large file is going to be 1 GB, right? So let's pick up the first file and let's see what happens. The first file, Parquet number 7, is picked up and it is simply placed in the first bin. And this is 1000 megabytes of size, out of which 320 has been occupied now. Now let's pick up the next one. The next one is 310 megabytes. Of course, the first bin has that much of size, so it is going to be placed in the first bin. Now let's go to the third one. The third one is 280 megabytes. This does have 280 megabytes of size, so it is going to be placed in the first bin again. Now the first bin has only 90 megabytes of size left. Now let's go over to the next file, but the next file is 270 megabytes. So for this a new bin is going to be created, right? So it tries to put it in the first bin, but it cannot. So that is why a new bin is created. Yeah. Now let's go over to the next file. The next file is 220 megabytes. The first bin only has 90 megabytes. So that is why it's going to be placed in the second bin now. Yeah. Now let's go over to the next Parquet file, which is Parquet number 9. 190 megabytes of size. It cannot be placed in the first bin. So let's see that it cannot be placed in the first bin. So it goes over to the next bin. Yeah. The next Parquet file is 180 megabytes of size. Again, it cannot be placed in the first bin and it should go in the second bin. Next one again, 160 megabytes of size here, cannot be placed in the first bin. How much size does the second bin have now? It has 140 megabytes of size left. So it cannot be placed in the second bin also, right? So it goes to the second bin, but it cannot be placed. So that is why a new bin is going to be created. Yeah, simple. So let's go over to the next one, 150 megabytes of size. It cannot be placed in the first one, cannot be placed in the second one also, but can be placed in the third one. Yeah. Let's go over to the next one, 130 megabytes. Cannot be placed in the first one, but it can be placed in the second one, right? Because the second one has 140 megabytes of size left. So it is going to go in the second bin, right? Let's pick up the next one. Again, it cannot go to the first bin. It cannot go to the second bin. So it is going to end up in the third bin. Now the last one, we see that the first bin does have 90 megabytes of size left. So it is going to end up in the first bin itself, right? And that is how we see that 3 bins are created nearing 1 gigabyte of size, and all of the files, you had so many files, it has been reduced to smaller number of files, right? So now if we correlate this back to the PDF example, instead of opening 300 PDFs one by one, probably you will have 4 to 5 PDFs. Right? Okay, so now let's see all of this in action, and for this I'm going to create a notebook, a new notebook, which is going to be named 07 optimize, right? And let's use this data set that we've already been using earlier for quite a good number of time. So let's simply do a spark.read.parquet, and together with this, let's also display 5 rows from this data set. Yeah. So now while we are doing this, let me also print the total number of rows, and along with that, okay, so here is what it looks like, and let me also do a df.select category dot distinct dot count, right? So the reason why I'm doing a distinct of the column category, which has 8 unique categories, is because I want to partition by this column, right? So let's quickly do a df dot repartition 5 dot write dot mode overwrite dot partition by, we partition by the category column dot save as table, and I'm going to simply save as delta catalog dot delta db dot optimize example1, right? So let's just save it like this. And the reason why I'm doing a repartition 5 is because I want to mimic the small file behavior. So each of the partitions that you see over here that is going to be created for the column category. So you're going to see one partition for clothing, one partition for toys, and so on. Each of these partitions should have 5 files. Yeah. So let's go ahead and run this. Okay, so this is complete. Let me go to the catalog and I simply take this up, take the table ID, and let me go to the container tables, and then here is this table, and you see all of the partitions over here. Each of these partitions should have 5 files, right? There you go. So you see 5 files over here, and that is because of the repartition 5 that we put over there. Yeah. So now let's run a query, and let's also time this query. Let's do a df example1 equals this, I read in the table, and let's say df output equals df example1 dot where df example1 dot category equals clothing dot collect, right? And let's also print. Okay, let's go ahead and run this now. So let's run this and see what happens. What is the total time that is taken? 2.3 seconds is the total time that is taken to run this query, right? Now let's go ahead and run a compaction on top of this table, right? So basically the 5 small files that we see, that should be combined into one bin, one file, as a result of this optimize operation. So we simply do from delta.table import delta table and table equals delta table dot for name. Okay, this is great. That is what I wanted to run. So let's go ahead and run this. Yeah. Perfect. So now this is complete. What I should see over here is instead of 5 files, I should see just one file because they've all been compacted into one file, right? So let me run a refresh. Okay, so now instead of one file, I see 6 files, right? All of the files were written at 1855-15, but then there is this one file which just got written now at 1857-31. And if you look at the size, right, the size is bigger than all of this, right? So what happened is it combined all of those 5 files into one file, right? And this file right here is that one file. What happened to the other files? They still stay there, but they have been tombstoned. What tombstone means is that they have been marked for soft delete, right? So if you look at the catalog over here, sorry, the delta log over here, not the catalog, what we should see over here is if I were to look at category clothing, we see that there are 5 removes. Yeah. And there should be one add because it removes those 5 small files from the log and then it adds one file. So here we should see one add for the add operation for the clothing category. Yeah. And this is the new file that got added, right? So I hope that makes sense when you compare it with the delta log. Now, how do you remove those 5 files which is no longer going to be referenced in the latest version? We'll come to that. Now let's go back and let's run an operation called vacuum, right? So what vacuum is going to do is it is going to remove the files for tombstoning, right? The files that have been tombstoned or marked for soft delete, they are going to be removed. Yeah. So in order to do that, we simply run a table dot vacuum and I put a number 0 over here. 0 basically stands for retention duration. Generally, the retention duration is 168 hours. So files that have been created within the last 168 hours are not going to be deleted. But when I put a number 0, it simply says that go ahead and delete all of the files that have been tombstoned or have been marked for soft delete. So let's go ahead and run this. Okay, so it gives me a warning saying that are you sure that you would like to vacuum file with such low retention duration? And it's really good that such a warning is in place, right? Because somebody may be just running a vacuum by mistake. So what we need to do is, if you're certain that there are no operations being performed on the table, such as blah, 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 then you may turn off this check by setting this, right? And as I was saying earlier, if you're not sure, please use the value not less than 168 hours, right? 168 hours happens to be the default. So let me go ahead and run this. And this is going to be a set. Let's run this now. And let's run the vacuum now. Yeah. Okay, so the vacuum is complete now. Now, if I were to go back to this table, and if I were to open any of these categories, ideally I should see just one file, because all of the 5 files were compacted into one file, right? And that is what you see over here, right? Let me also check the other ones. Okay, perfect. So this works as expected. Let me also rerun this query on this table after we've run an optimize and a vacuum, right? So let's go ahead and run this again. Okay, so the wall time is now 1.4 seconds comparing to 2.3 seconds earlier. So there is an improvement in the runtime, right? Of course, the number is not very huge because our file sizes are very small. We will be able to see significant improvements on a larger data set, right? But overall, the idea is to help us understand that small file problem is a significant problem, right? And optimize helps us eliminate that problem. Okay, so now I want to share with you how to use predicates or filters or where conditions with optimize. So this is going to be very helpful in cases where you have incremental data coming in. Let's say you have daily data coming in, right? You have one partition for each day. You would naturally want to run an optimize on that particular day, on that particular partition. You don't want to run optimize on the full data. Yeah. So in those cases, we would want to use a predicate or a filter with the optimize. Yeah. So let's try to mimic that situation, and I'm going to use the same data frame df over here. So let's assume that I'm creating a new category called fruits, and this is simply going to be, so I'll just take up one category and rename it, right? Just for the sake of simplicity. So df.category equals fruit. This is actually this, I'll take up clothing, all of the data that exists in clothing, and I'm simply going to rename it as fruit. Okay, and this is simply going to be from PySpark .sql .functions, import PySpark .sql .functions as if. Yeah. So let's go ahead and run this. So basically what I've done is I've taken all of the data that exists for the clothing category and simply renamed clothing to fruits. And this is just to generate some sample data. So what this means is that a new category or a new partition is coming in, which is by the name fruits. And now I simply want to optimize that partition. Yeah. So let's go ahead and first check that this only contains one category. Okay, So it simply contains one category, right? Now let me go ahead and write this data. So I'm again going to do a repartition 5. Okay, great. So this should write a new partition to this table. Yeah. So let's go ahead and run this. And now I should see a new partition called fruits over here once this completes. Okay, so the writing has completed. Let me refresh this and I see a new category called fruits. Now let's go here and I see 5 files over here. Yeah, as expected, because I did a repartition because I also wanted to mimic the small file problem. So now what I'm simply going to do is I'm going to run a table dot optimize dot where the category equals fruits and then execute compaction, right? You can also use SQL in order to do this, and for this time let's use SQL. So the command is going to be something like this: optimize delta catalog dot delta db dot optimize example1 where category equals fruit, right? Let's go ahead and run this now. Okay, so this is complete. Now I should see one extra file over here, and you see that there is this one extra file that is created. Yeah, and now I simply want to remove all of the tombstone file. Yeah, so again let's use SQL for now. Vacuum this table delta catalog dot delta db dot optimize example1 retain 0 hours. So you get a gist of using both SQL and the delta table API. Yeah, so let's run this. Great. So now you see that we have only one file as expected. Yeah. So that is how you can use predicates when using an optimize command. So given that now we've seen the small file problem in action and how to fix them using the optimize command, let's also understand the root cause, right? Because many a times if you understand the root cause, you may fix the problem right at the source or the origin, right? So let's have a look at the root cause one by one. The first one is, first of all, let me quickly write root causes. And the first one is repartitioning to a very large number, right? The first one is a repartition. So let's say that you have a file which is 10 gigabytes, right? And you end up repartitioning it into 10,000 parts, right? So what you do is you do a dot repartition, you do a dot repartition of 10,000 on whatever data frame that you're running, right? So if your data set is 10 gigabytes in size, you are essentially going to end up with 10 into 1000 megabytes. I'm assuming 1 GB to be 1000 megabytes for simplicity, into 10,000, which is simply 1 megabyte in size, right? So each of these partition is going to be 1 megabyte in size, and that is going to cause the small file problem. Yeah. The second one, the second issue is partitioning on a high cardinality column, right? You partition on a high cardinality column. And by high cardinality, I simply mean that this column has a lot of distinct values. So let's imagine that you have a 500 MB retail dataset, right? You have a 500 megabyte retail dataset, and you have a category column. So for some reason, you want to partition by the category column. Let's say you are writing this data set, and when you do a df dot write dot partition by you basically put in the category column, right? And this category column has a lot of distinct values. So let's say it has thousands of distinct values, right? So what you're going to end up with is a lot of small files, and this again will lead to the small file problem. The third one is frequently updated data sets, right? Frequently updated data set, right? So let's say you have data coming in continuously, and by continuously, let's assume that it comes in every 5 minutes, right? So these data sets that come in every 5 minutes, they basically end up writing small updates, right? And these small updates are going to be in the form of small files, right? Which is again going to lead to a small file problem, right? So as we can see that these three could be some of the most important root causes for the small file problem. And number one and number two, these are purely technical in nature, right? You can change the repartition number, or you can change the partitioning column in order to avoid it, right? Avoid the small file problem. But problems like this, where let's say the business needs to see data instantly, right? Or they want the data to be updated frequently. In those cases, these problems are not technical in nature. They are more of a business problem, right? So how do you solve such kind of problems? So what you can do essentially is, given that the team is going to use this underlying data set, you can choose to run optimize after a number of hours, or maybe every day, so that at the end of the day, you end up combining those small files into a larger file, right? Now, there are three methods or approaches that you can think about whenever you want to run the optimize command. Yeah. And the first approach or method is manual optimize. And we've seen it in the code example where we simply run the optimize command. We specify the table, and if needed, we specify a predicate, right? So either you can run it like this, or you can run it like this, right? So this is the most simplest approach that is widely followed. Now the next approach is an automatic one and is called optimize write. Yeah, it's called optimized write. What optimize write does is that it simply combines all the small writes to a partition into a single write command. So we are going to understand what that means, but let's say we are doing the traditional write. What simply happens is that for creating one partition, and let's imagine that this is the date partition, something like date equals 2025 0501. Yeah. So in order to create this partition, there are several processes which are writing to this partition. So we see that executor number one is writing to this partition. Executor number two is also writing to this partition. Executor number three is also writing to this partition. And these may end up writing small Parquet files. Let's say this is 1.parquet, this is 2.parquet, and similarly this is 3.parquet. So these may end up writing small files, thereby creating the small file problem, right? So the root cause of it is several processes writing to a partition. Yeah. Now instead, if you look at optimized write, what's going to happen is that all of the data is going to be shuffled and then it's going to be executed as a single write command. So all of the data is shuffled over here from executor 1, executor 2, and executor 3. All of the data is shuffled, and then this is executed as a single write command. Yeah. So a very important point to note here is that it's executed as a single write command, and this is going to produce appropriately sized files, right? So this is going to produce appropriately sized files in partition 1, 2, and 3. Yeah. So that's the benefit of using optimize write. However, a trade-off is that it's going to incur a shuffle. It's going to incur a shuffle, and we know that shuffles are costly because it requires data transfer, right? So it's important to keep this in mind whenever we want to use an optimize write. What are the things that you want to optimize for? Yeah. Is it write latency? If it is write latency, then this might not be a good solution because there is going to be some shuffle involved and that is going to take time. If it's optimizing for the small file problem, then of course this is a very good solution. So now let's see optimize write in action. And for that, I'm going to use the same data frame over here. So let me quickly create a new table, df dot repartition, and for this time let me create lots of partition. So let me repartition by 288 and then write dot mode overwrite dot partition by category, and then let's save as table delta catalog dot delta db dot optimize example2. Yeah. So let's run this, and on this table I also want to run this query, the same query that I've run earlier, and see how it performs. So this is going to be example2. Yeah. Okay, so now that is complete, I should see a table called optimize2 over here. And if I go to the details, let me have a look at the table over here. And okay, so I basically see all of these partitions over here. Yeah. So ideally there should be some 288 partitions. So now let's go ahead and run this, and let me create another table. This time after partition by, I am going to write an option which is going to be optimize write to be true, and then we are going to save this table as example3. Yeah. So let's go ahead and run this. So this operation has taken 6.97 seconds. Yeah. Okay, so this is completed. Again, I should see a new table here, which is optimize example3. And if I have a look at the table this time, I should see minimal partitions, right? Okay, so now when I look at these partitions, we see just one file. So that means the optimize write has worked very well, and it is not writing small files. It is just written one file which is appropriately sized. Let's also run this operation once again, and this time on example3. Perfect. This runs a lot quicker. You see 6.97 seconds versus 1.82 seconds. So now we've seen and understood optimized writes, and it's actually good for cases where many processes or executors are trying to write many files to a partition. And instead of all of that, we shuffle all of those files, we combine all of it, and write it into appropriate file sizes for every partition, right? So every partition is going to have an appropriately sized file, and there is going to be an appropriate number of those files, right? So this helps avoid the small file problem. But in cases where we are frequently writing small updates to a table, right? The updates to a table are coming in small chunks. The files that we get out of those small updates are still going to be small files, right? So we still end up with the small file problem. And here is where auto compaction comes into picture, and that is the third approach that I wanted to talk about. So what auto compaction does is that what auto compaction does is, and let me quickly write something here, is that let's say when you get small files, right, you get a few files, after every write it is going to run a compaction operation, right? It is going to run an optimize command which is going to compact all of these files into appropriately sized files. That is what auto compaction exactly does, right? Now it's really important to understand is that auto compaction is not going to run for an arbitrary number of files. Let's say you got two files and now you want auto compaction to run and combine it into one file. Basically there is a setting which is called spark.databricks.delta.autocompact.min files, min num file. So just Google it up. You can specify the minimum number of files that need to be present in order to trigger auto compaction. Once that is there, it is going to compact all of those files into appropriately sized files, right? So let's see auto compaction in action right now. And we are going to use the same table, example 3 as earlier. And before I can use that, I need to do two things. The first one is to enable auto compaction, and the second one is to disable optimize write, because if I don't disable optimize write, it is going to take all the small files, shuffle it into one, and then write it as one file. So I won't be able to see whether auto compaction is working or not. Yeah. So first of all, I disable this, and then let's enable this. Actually, let me change this auto optimize the dot auto compact. This is going to be true. Yeah, perfect. Okay, this is done. Now I want to check another property which basically tells me spark.databricks.delta dot auto compact dot min num files. This basically tells me what is the minimum number of files that I need in order to trigger auto compaction. So I actually recently changed it to 3. The default number is 50. Yeah, so I changed it to 3. You can change it to 3 using the following command, using a set. Yeah, so that is how you can do that. Now I want to insert a new partition into this table. Yeah, and for that I'm going to use the fruits code again. So let's assume that there's new data coming in, and let me simply rename this to detergents, and let's also rename this to detergents. And again, this is just for creating sample data. I am simply taking up all of the rows with respect to the clothing category and then simply renaming the clothing values to detergents, right? So let's go ahead and run this. And now I want to run a df detergent dot repartition 5 dot write dot mode overwrite, and this is going to be written as example 3. Yeah, so let's go ahead and run this now. Okay, so this is complete. Let's check what happened. Okay, so I see a detergents category and I see 1 2 3 4 5 6 files, which is exactly what we wanted. The reason for that is it would have written 5 files initially because we had a repartition 5, and then it wrote an additional file because of the compaction operation. Yeah, so what you see over here is essentially there is one file which is bigger in size, which is this one, and this was the one that was written as a result of the auto compaction operation. So that is how auto compaction works. And all of these other files, right, that you see over here, they have been tombstoned. When you run a vacuum, all of them could be removed, right? So I hope that gave you a gist of how auto compaction works. So now let's move over to the next topic, which is called vacuum. And we've already seen vacuum in action. So whenever we delete, update, or merge records in a delta table, some of the underlying records are going to be removed, right? So when you update, it creates a new record and the old records becomes irrelevant. When you delete, all of those records become irrelevant, right? So because these records have become irrelevant, they are supposed to be deleted, right? But what actually happens in Delta is that it doesn't physically delete it from the cloud storage or from the disk. It just marks it for deletion, right? It just tombstones it, or it does something which is called soft delete, right? So all of these rows which are marked for deletion, which is soft delete, or the rows which have been tombstoned, they can only be removed once you run a vacuum, right? So what essentially happens is, let's say when you run a delete, merge, or let's say an update, there are rows which are going to become irrelevant, right? And those rows are simply tombstoned, or they are marked for soft deletion, right? So the moment you apply a vacuum, or let's say you want to remove these rows physically from the disk, physically remove all of these rows either from the cloud storage or from the disk, right? So in order to do that, you need to run the vacuum command, and vacuum is going to remove all of the rows which have been tombstoned or have been marked for soft delete, right? Essentially the same thing, right? So that is how vacuum works. And there are two important points to note. The first one is that vacuum helps you save on storage cost. It doesn't make your queries faster. It's a very popular misconception that running vacuum is going to make your queries run faster. That's not the case. The reason for that is we've seen in earlier examples that we had 5 files, right? We have written 5 files, and then we run an optimize, and then it compacts all of the data into one file, right? So now you end up having 6 files, right? 5 files which were already present earlier, and additionally you have one file which was a result of the compaction operation, right? So now the 5 files have been marked for deletion, right? So this is the 5 file and this is one file. This has been tombstoned and this one is active, right? So the moment you run a vacuum, it is going to delete all of these files. It is going to permanently physically delete all of these files, and the file that you are left with is this one file. So the data you end up scanning is just the same, right? The filtering and all of that happens at a delta log level, right? Which files do I need to scan? That happens at a delta log level, and that is taken care of over there, right? So essentially, when we run vacuum, we just save on storage cost. We are simply removing data, and that is how it doesn't make your queries run faster. It simply removes data that is not needed. And the second point is that it limits your ability to time travel. Limits your ability to time travel. So if you run vacuum, you will not be able to go back to any of the previous version. So let's see that with an example. So I'm simply going to take one of these files over here and let's create two data frames, right? Equals spark dot read dot parquet and this is going to be a filter f dot column customer id dot between. This is going to be 101 and 150, right? So this Parquet file contains all customers from 101 to 200. So I am simply selecting 101 to 150, and this is going to be 151 until 200. So this will be 151 comma 200, and let's go ahead and run this. Let's now write this to a table. Yeah, so this is going to be write dot mode override. I don't need any partitioning, and let's just say vacuum example1, and let's just write it. Yeah, let's also see the history. Describe history delta catalog dot delta tb dot vacuum underscore example1. So I should just see one row. Okay, what is the issue here? Okay, that's a spelling mistake. Vacuum underscore example1, and this is as expected. So now let's write the other data frame as well. Yeah, and this is simply going to be df151, and I'm going to append it. Let's go ahead and write it again. Okay, perfect. So now we see two rows. The first one is the create, the second one is the write operation, where we wrote an additional 50 rows of data. Now let's go ahead and do a delete. Yeah, so actually before I do a delete, let me show you something. So this is the vacuum table. Let me copy the UUID, and okay, so I see two rows over here. Yeah, the first one, which is 22, 21, 23, the time at which it was written, this will be this file over here, which contains all of the customers from 101 to 150, and the second one should be 151 to 200. Yeah, so the second one over here should be 151 to 200. Yeah, the one that starts with C82. Okay, now let's go ahead and delete some rows. So we do a delete from delta catalog this, where customer ID between 151 and 200. So customer IDs from 151 to 200, they basically reside in this Parquet file right over here. Yeah. So when I run this statement, ideally it should tombstone the second file. It should mark it for delete. Yeah. So now let's run this again. Let's see the history again. Perfect. Now you see three statements or three versions. Yeah, the third one is a delete. After this, let's run a few quick statistics, which is minimum of customer ID, comma maximum of customer ID from this table, vacuum example1. Yeah, what should we see? So we have all the customers from 101 to 200, and we have removed 151 to 200, right? So we have removed 151 to 200, so we should see the minimum to be 101 and the maximum to be 150, and that is what you see over here. Now if I were to run the same statement on version number 1, we ran a delete on version number 2. If I were to run the same statement on version number 1, it would have all the rows from 101 to 200, right? So the results would be a little different. The minimum would be 101, but the maximum would be 200. Yeah, perfect. So now what we want to do is we want to run a vacuum. Yeah, we want to run a vacuum in order to remove the tombstone file.
over here. We want to remove this file over here, which has been tombstone. So let's go ahead and run a vacuum delta catalog dot delta db dot vacuum retain 0 hours. Yeah, so let's go ahead and run this. And as expected, I got a message saying that are you sure you want to delete this? And we've seen this earlier as well. So let's go ahead and disable this check over here. So we simply do this equals false, and let's run this again. Okay, so now the vacuum operation is complete, and I should just see one file over here, the one that starts with 8EF, right? The second one should be gone. Perfect. So that is what was expected, right? So now that the vacuum operation is complete, if I were to run a history, if I were to see the history of this table, describe history, I am basically going to see two additional rows. The first one is for vacuum start and vacuum end, right? So now we see over here that we only have one Parquet file, and this corresponds to the data from customer IDs 101 to 150, right? So the experiment, what I want to do is select star from this table version as of, yeah, and I want to play around with these numbers a little bit. So let's say if you do version as of 2, what should you get? Should you get any data or not? That's the first question. Okay, so ideally you should get data, because after this delete, all of the data from 151 to 200 were deleted, right? So the data from 101 to 150 was still present, right? And we still have the file that is needed for giving us the data from 101 to 150. Yeah, so this operation should just work fine, and it works fine. Yeah, so what will happen if you do version as of 1? Will this work? Take a guess. Okay, this doesn't work, because in operation in version number 1 we wrote a file which contained data from 151 to 200, and that file has gone missing. So that is why the data that was contained in version number 1 is incomplete, and that is the reason why we cannot go back in time in order to access this. Yeah, let's see about version number 0. Again, take a guess what would happen over here. Okay, you already have the Parquet file for version number 0, because we wrote the data from 101 to 150, and that can be accessed because of the Parquet file that we see over here. Yeah, so that is how time travel is going to work with vacuum, and you need to be a little careful if we want to go back in time and access data points, right? So we need to run vacuum very carefully. So the next optimization technique that we are going to talk about is ZOrder. Yeah, it's called ZOrder. But before we understand what exactly this is, let's actually set some ground. Let's set some context with this example. Yeah, so let's say you have a bunch of files that you see over here, 1, 2, 3, and 4.parquet, and these are currently sitting on your disk, either on your disk or on some cloud storage, and you basically want to process them, right? You want to process them, and in order to process them, these have to be loaded in the memory of whatever compute you are using, right? So these have to be loaded in memory. Now, in order to load it into memory, there has to be a costly data transfer over the wire, right? So in order to do that, let's first take this example where we have a query coming in from the user. The user basically asks that give me all of the records where age is greater than equal to 5 and less than equal to 10. Yeah. So for each of the Parquet file that we have over here, we have stored some statistics. And we already know that all of these statistics are stored in delta log, right? The minimum, maximum count of values for all of the columns, right?
So we've put the statistics over here, and we will use this in order to figure which of the files need to be transferred over the wire. Yeah. So we see that the minimum age and the maximum age is 4 and 12, which overlaps with this value, right? So that means that this file is going to be transferred. This file is going to be transferred over the wire. Here we see that the minimum is 10, maximum is 28, and that overlaps with this value. So this file is also going to be transferred. Again, the minimum is 6 and 14, that also overlaps with this value. Yeah, with this value here to here, and this file is also going to be transferred. And this is a wide range from 4 to 60, and this again overlaps with this value over here. That means 4.parquet is also going to be transferred. Yeah. So essentially what we see is that when such a query comes in, all of these 4 files are going to be transferred. Yeah. These are going to be transferred over the wire, and this is a costly operation. This is a costly operation. Now, if we were to take a step back, do you think this transfer can be avoided? Instead of transferring all of the 4 files, can we transfer fewer files? Is it possible? Take a moment and think about it. So with this data layout, it's actually impossible to avoid sending any of the files over the network, right? We cannot omit to send any of the files over the network. We have to send all 4 of them. If we omit any of them, then we won't get the right answer to this query that the user has asked, right? So what is the alternative? How can we avoid sending any of the files over the network? Is that even possible? How do we optimize for that, right? So in order to do that, that is where ZOrder comes in. So first of all, let me take some of these numbers, the minimum and maximum, right? So let's say we have 4 over here, we have 12 over here, and of course between them there is going to be several keys, several values for age, which I'm not writing down, but we will have all of those values, right? And then we have 10 and 28. So 10 is going to be over here, and let's say 28 is going to be over here. And then we have 6 and 14. So 6 is going to be over here, 14 is going to be over here, and then we have 4 and 60. I've already noted down 4. So 60 is going to be somewhere over here, right? And between all of them, right, there is going to be some keys which we do not know, but we are aware that there is going to be data in between them, right? So this is a sorted order that I've produced, right? So here is something that we can apply in order to skip files. And first of all, let me copy this. Let me copy this here. Yeah. So what essentially I'm going to do is that I am going to take the first few values, which is from 4 to 10, and I'm going to put it into one file, which is 1.parquet. And then I am going to take other few values, which is from 10 to 28, and then I'm going to put it into 2.parquet. The intuition behind this is to avoid overlaps between the file, right? If there are minimal overlaps, probably I'm going to select only one file where all of my data is going to reside. Yeah. The next file I'm going to choose is, so probably we'll have this number 29 over here, and then 50 somewhere down the line over here, right? So 29 to 50, I am going to place this in 3.parquet. And then we are going to have this number 51. Let me place it over here. We're going to have this number 51 and until 60. I'm going to take all of this data and then put it in 4.parquet. The goal and idea behind this is to avoid overlaps between the file. The lesser overlaps are, the lesser files you need to scan, right? You will be able to prune the file. You would be able to say that, okay, this is the file I need, and let's send this over the network, right? So ZOrder is basically a sort and repartition. So here all of the data has been sorted by whatever key we wished, right? In this case, the query that has come in, and we basically repartition the data into those number of files, right? So that is the logic and the idea behind ZOrder. And what it does is that in these files, it simply co-locates data. By co-locate data, what I mean is similar data is placed in the same file. So similar data is placed in the same file. Now let's go ahead and have a look at this, how this query is going to behave now. Yeah. So now, where age is greater than equal to 5 and less than equal to 10, does it overlap with this? Yes, that means this file is going to be transferred. Does it overlap with this, which is 2.parquet? Yes, it does. This value and this value overlaps. That means this parquet is going to be transferred over the wire. But does it overlap with these two? The minimum itself is 29 and 51 over here. It doesn't. So that means we've avoided sending these two files over the wire. It has been pruned. It has been filtered that we don't need these two files, right? And that is one of the benefits and beauty of the order. It co-locates similar data in the same file, due to which this becomes possible. So to keep things simple, I have taken a single dimensional example wherein we refer to the column age, but this very well applies to multiple dimensions, right? Where we would like to filter by multiple columns. And the idea is very simple. The idea is to take all of these columns that we want to filter by and then map it to single dimension. So all of these columns, they are multi-dimensional, right? More than one column, it's multi-dimensional. So we take all of these columns that we want to filter by, right? So we take all of these columns and then we map it to a single dimension. We map it to a single dimension. And how does this happen? It happens when we put this inside the ZOrder function, right? When we apply ZOrder on the set of columns, right? And this basically preserves the locality. When we apply ZOrder on the set of columns, it arranges the data layout in such a way so that the locality is preserved. And by locality, what I mean is that similar data points are close to each other. So ZOrder basically preserves locality. And by preserving locality, what we essentially mean is that similar points, similar data points are in the same file. Actually, not necessarily always in the same file, because in the earlier example that we saw, the value, the age 10 was in 1.parquet, and then the age 10 was also in 2.parquet. The idea is to avoid overlaps, to keep overlaps as minimal as possible, right? Because we also don't want one file to have enormous amount of data. Yeah. So I'm going to take another example where we are going to have two columns, which is product ID and quantity. And for some reason, we write a lot of queries, a lot of filters on these two columns. Yeah. So we write a lot of filters on these two columns. So what we want to do is that we want to ZOrder by product ID and the quantity. So when we essentially do this, what it does is that it takes these 2 points from the two-dimensional space and then it applies a ZOrder. What ZOrder is essentially a space filling curve which maintains locality. Yeah. So just to iterate again, what it does is that it is going to map this two-dimensional value, which is, let's say, this value, and all the other values that you see over here. It is going to map two-dimensional values to a single dimensional value. Yeah. And the beauty of this curve ZOrder, is that the points which are close in the two-dimensional space, they are also going to be close in the single dimensional space. So the points which are close in two dimension, when you map it to a single dimension, they are also going to be close. Yeah. So for argument's sake, in order to make you in order to help you understand this better, let's say what ZORDER does is that it simply adds values, right? And this is just to make you understand things better. Yeah. So let's take all these values, the values which have product ID equals 10, and let's simply add them, right? So this is going to be 15, this is going to be 19, this is going to be 18, this is going to be 22, and this is going to be 14, this is going to be 12, and this is going to be 11. Now what I do is that I start putting the data points from the lowest to the highest by Z order, right? So the lowest is this one. I basically put 10 and 1 over here. Then we have 12. I put 10 and 2 over here. Then we have 14. I put 10 and 4 over here. Similarly, 10 and 5. And then 10 and 8. This one over here. And then 10 and 9. And then finally 10 and 12. So what we see is that points which are close in the two-dimensional space, which is 10 and 1, this is very close to 10 and 2, they are also close in the single dimensional space after doing a Z order, right? So 11 and 12 are close. So if we put the values over here, they are close. These are placed close to each other, right? Just one row apart, right? So this makes sure, Z order makes sure that when points are reduced from a multi-dimensional space to a single dimensional space, they are co-located, right? They are close to each other. And using this, we simply create the files. We place all of this in one file over here, and then all the other data, which is again co-located, is placed in this file over here. Now we don't want to create one Parquet file for 11 and 12 and 15 because of course we don't want to end up with the small file problem. We want this data to be appropriately sized. Yeah. So that is why we don't create one file for each of these values. So I hope this gives you some kind of intuition on how ZOrder works internally. It basically brings similar data in the same file, sometimes not always in the same file, because again, as I discussed earlier, we don't want to put too much of data in the same file, right? If we had a lot of rows for number 10 over here, product ID number 10 over here, probably some of them would have also have gone over here in the second file, right? Because we don't want one file to have enormous amount of data. We want it to be appropriately sized. Yeah. So it co-locates similar data in the same files, and the goal is to skip as much amount of files and data points as possible. And that is going to help us run our queries faster, scan lesser number of files, and send lesser amount of data over the wire. Okay, so let's see ZOrder in action. And for that, I'm going to use this file again. So let's go ahead and read this. Spark.read.parquet and this file. And this time I am going to select few columns only. It is going to be customer ID and the category price, quantity, and invited. Perfect. So let's go ahead and run this, and let me do a df.limit of 5. Okay, and I want to generate a lot of rows. So what I'm simply going to do is I'm going to run a loop. Expected rows equals 20 million. So we simply do 20 0 0 0 0 0 0. Okay, and now while df union dot count is less than equal to expected rows and df union equals df union. So I keep unioning the same data frame in the loop, and the count is simply df union dot count, and I copy this and put the final count to be this one. Okay, now I also want to write this data frame to a table, save as table in our delta catalog dot delta db dot zorder example1. Yeah, Okay, so this is complete, and now we are writing it to this table. While this is going on, I want to write a query basically to see how long does it take to run, right? And this is simply going to be select category comma sum of price into quantity as total sales, right? As total sales from this table right here, from this table where customer ID equals 201, group by category, right? So I'm purposely doing a filter on customer ID equals 201, and we are going to compare the performance of this query after a ZOrder has been applied. Yeah. Okay, so the write is complete. Now let's go ahead and run this query. And let me also, okay, so the wall time is 785 milliseconds. And let me also see how this table looks like. I'm going to take the location from here and basically check over here. Okay, so here it is. And then it created a lot of files. And let me download the Delta log over here. And let's open it. So it added how many? It added 255 Parquet files. Yeah. And what we see over here is that each of these files have a minimum value for customer ID, which is 201, and a max value of 99457, right? So if I write a query, which is something like this, where customer ID equals 201, it is going to scan all of those files, all of these 255 files, because the minimum value of customer ID in each of these files is 201 from 201 to 99457. So it ends up scanning 255 files. Yeah. Now let's go ahead and run and optimize, right? A Z order with an optimize. So optimize this table Z order by customer ID. Now Z order and optimize go hand in hand, right? Whenever you want to run a Z order by, you run it together with an optimize. Optimize is going to create larger files, right? It is going to merge all of the small files into a large bin or a large file. And while this process happens, while it is putting the small files together, ZOrder is going to co-locate similar data. Yeah. So that is the reason why they work hand in hand, they work together. So you can either use this SQL, or you can also do this. So from delta import delta.tables, import delta table, and we simply do table equals delta table dot for name, and then table dot optimize dot execute Z order by, and then we put in the customer ID over here. So you can use any of these two approaches. Yeah. So I'll comment this for now, and I will go ahead and run this. Okay, so the Z order is complete, and if I were to look at some of the metrics, what it says is that number of files added is 2, and it removed 256 files. Yeah. So we're going to look at all of that, but before we do that, let me run this query again, and let's compare the runtimes. Yeah. So let's run this query. And it is 144 milliseconds, and the last time was 785 milliseconds, close to 6 times of improvement. Yeah. And that's a significant improvement. Let's also see what happened behind the scenes. So if I just refresh this, and if I download this log, let's download this and let's have a look. So all of these files which were earlier added, there is a remove for all of this, right? And we have add for only 2 of them. That means 2 new Parquet files have been added. And let's quickly have a look at the statistics. So minimum value for the customer ID is from 201 until 48632. And the other file is from 48632 until 99457, right? So this is something really amazing that has been done. What it first did is that it removed all of the 255 or 256, whatever number of files were there. It removed all of it, and then it compacted the data into 2 files. That is where the role of optimize comes in. And then similar data was co-located, right? It co-located data from 201 until 48632. The remaining was put in the other Parquet file. Now I don't need, so initially what I was doing is, okay, I don't have that statistics over here. Let me go over here. Initially what I was doing is I was scanning all of the files, right? I was scanning customer ID 201 in all of the files, right? Because the minimum value told me to do so. Now I just need to scan just one file, right? And that's a remarkable improvement. So that is how ZORDER works, and I hope that gave you some insight into all of this, right? So now let's talk about how do you apply ZORDER together with Hive style partitions. Yeah. So let's try to mimic that example, and I'm going to use this data frame over here. So this is going to be, let's try to create those partitions. Dot mode override dot partition by, and let's partition by invoice date, and let's save this table as delta catalog dot delta db dot zorder example2. Yeah, so let's go ahead and run this, and it should basically create partitions on the invoice date. Yeah, so now we've earlier seen that we applied zorder on the customer ID. So generally there's a pattern that people follow is if we have a Hive style partition on, let's say, the invoice date, and we can use this together. We can zorder by the customer ID for each of those invoice date. Yeah, so we can zorder by customer ID for each of those invoice dates. Yeah, so now let's imagine that a new partition is coming in, and let me quickly write some code to mimic that. So we are going to do df.filter f.column invoice date equals 2023-01-01. So I basically take in all of the data for that day, and I just rename it. I rename it to 2025-0504. Yeah, so I'm basically taking in all of the data for some day, and then I'm just renaming it to today's date. And this is simply to create some new data, mimicking the fact that new data came in today, and now I want to write a new partition to my table. Yeah, and that table is basically this table. So let's also see how this looks like. So basically this table has all the invoice dates, right? And new data has come in for today, and I want to basically write this data to this table. Let's quickly check that there are records over here in this table, and then okay, perfect, we do have records. So now let's go ahead and simply write this, write dot mode append and then partition by invoice date, and then save as this table, right? So this would mean that we just wrote in a new partition, and let's also verify that. Select max of invoice date from this table delta catalog dot delta db dot zorder example 2, and that should show us this new date that we put in, which is the same. Now let's go ahead and apply a zorder. So we are going to use it together with an optimize zorder by customer ID, but we only want to do it for the current invoice date. Yeah. So the current invoice date equals 2025 05-04. Yeah. So we have our Hive style partitions, and given that we know that our queries, for whatever reason, is a lot on customer ID, we Z order by customer ID, and this is also a pattern which is widely used. And in your pipeline, when you are running your pipeline on a daily basis, you can simply parameterize this. You can simply parameterize this part of the command. You can simply put in current day -1, right? Because let's say you run this pipeline on yesterday's data because you have all of that data. Yeah. Now let's talk about the final optimization technique, which is liquid clustering. Yeah. So by now we've seen things like Hive style partitioning, where each partition value gets its own folder and all of the records for that partition value goes to that folder. And this essentially speeds up queries. On the other side, we have ZOrder, which optimizes your data layout. It co-locates data so that we can pick up relevant files, right? We pick up minimum number of files and then we scan them, right? So all of this makes your queries faster. However, the biggest problems with this approach is that they are not flexible. Yeah. So let me note all of this down. So the first one is Hive style partitioning. Hive style partitioning, and the second one is ZOrder. Now the problems with these two approaches is that they are not flexible. They are not flexible. And when I say that they are not flexible, what I mean is that you have to decide your partitioning column or ZOrder column up front, right? These two have to be decided up front, either whenever you do the partition by and the column name, or the ZOrder by and the column name. The column has to be decided up front, right? Now the disadvantage with that is, if today your filter pattern is by a column called country, and few months down the line it changes to another column called category, the layout of your data is by country as of now, right? It is optimized in such a way such that whenever somebody queries by country, it's very easy to find the records. But when the filter pattern changes over time, when it changes to category, that data layout is no more helpful, right? So essentially what you end up doing is you'll probably end up scanning the whole data set and the data layout is no more helpful. What you essentially need to do is you'll end up rewriting data according to the new filter pattern, which is by category, right? So that is the biggest disadvantage of these two approaches. Now this is where liquid clustering comes in, right? So it allows you to change the clustering columns anytime. Yeah. So it allows you to change the clustering columns. So this can be changed anytime, right? And that is the biggest benefit of using liquid clustering. It is very flexible in nature. It is incremental, meaning that you can change the clustering columns going ahead. Yeah. It is going to use, so let's say you have particular set of clustering columns, and down the line when you want to change it, it is going to use those new clustering columns in order to decide the layout of data. So the layout of data is then going to change going ahead. So the algorithm that liquid clustering uses under the hood, it maintains a balanced layout. And by balanced layout, what I mean is that it ensures two things. The first one is uniform file size, uniform file size, and the second one is appropriate number of files, appropriate number of files, right? So it is going to ensure that appropriate number of files are created. It doesn't end up creating lots of file with minimal amount of data. So that is where you avoid the small file problem. And it also ensures that those files are appropriately sized, right? So it ensures the number of files and the size of those files. And a good point to note is that in all of these files, your data is co-located, which simply means that similar data is going to reside in the same file. Yeah. So let's understand this with an example, and I'm going to refer to Denny Lee's blog, who's a developer advocate at Databricks and also a Spark and MLflow contributor. So here I'm in the blog, and let me quickly enable annotation. Let me zoom this a little bit. Okay. And here we go. So this was the diagram that I was referring to. So all of these boxes that you see over here, right? The boxes with the years put in over here, these are basically partitions, right? These are basically partitions, and these arrows that you see over here, these arrows, these are basically tasks. And in Spark terminology, a task takes up and processes one partition, right? A task basically takes up and processes one partition. And all of the partitions over here, as you see, they are uniformly or evenly sized. They are uniformly or evenly sized, right? So all of these tasks are going to complete almost on the same time, right? Because the amount of data that they are getting to process is just the same. Now, this is something that actually doesn't happen in a real world scenario. Let me show you what would happen in a real world scenario. So a real world scenario would look something like this. Probably one of the partition would have too much of data, and some of the partitions would have very less amount of data, right? So we see that 2023 and 2022 have a lot more data than the others, like 2020 and 2004. So these tasks are going to be on the critical path. So they are going to be on the critical path, and by that what I mean is that these two tasks need to complete in order for the whole job to complete, right? So these two tasks need to complete in order for the whole job to complete. Yeah, they are going to take the most amount of time. They are going to take the most amount of time. And the problem with this is that these two cores, the core processing, these two are going to be occupied while all the others are going to remain idle. They are going to remain idle. Yeah. So that is underutilization of your resources. Now, what liquid clustering is going to do is that it is going to combine all of the small partitions together into something meaningful, right? Into something meaningful. So this 2018 partition is as it is. It combined 2019 and 2004 into one, 2020 and 2021 into one, right? But we still face this problem because 2023 and 2022, these are still big fat chunks that one core or one task would need to process, and this is going to become a bottleneck because these guys have to do a lot of work. Yeah. So again, what liquid clustering does is very smartly it breaks it down, it divides the larger chunks into smaller buckets, right? So you see that 2023 had been divided into three parts and 2022 has been divided into two parts. Now the core which takes this up, the tasks which run over here, all of them are very uniformly sized. This becomes similar to the ideal case that we had over here, right? This ideal, so-called ideal case that we had, right? And therefore, my resource utilization is going to go up, right? And we are going to complete this job in a reasonable amount of time, right? Because every task or every core has got even amount of data to process, right? So that's the beauty of liquid clustering. And this example is on a single dimension. Let's see what would happen in multi-dimension. So let's say we want to cluster by 2 columns, and they are basically the year and customer, right? So in this case, we are also going to analyze the sizes for each of the combinations. And let's say that for year, I have 2023, 2022, and 2021, and these are my customers, right? So we see that these are the data sizes that have been marked over here, right? So red is small, yellow is medium size, green is optimal, and blue is Excel, right? So other than these two values for the year and customer, enterprise customer in 2023, this is optimally sized, and 2021 enterprise customer is optimally sized. All of the others, either they are small in size, the files are either small in size, or they are large in size like this one, right? So what is going to happen is that liquid clustering is going to combine the file sizes and make them appropriately sized, right? So something like this is going to happen. It is going to combine two medium size and one small size file, again two medium and one small size file, three small size and two medium size, and two medium and one small size file, right? So it is going to combine all of this and create one optimal size file, right? Now once this is done, we've seen that all of the files are now optimally sized except for this one. Now what it is going to do is that it is going to break this down into smaller file sizes. Yeah, so it is going to break this down into smaller file sizes, and the final result that we are going to get is something like this. So now we see that all of the files are appropriately sized, and we have appropriate number of files. And that's the beauty of liquid clustering. So it helps you achieve two things. The first one is the small file problem. So it helps you avoid the small file problem. We've seen several files which were marked red, right? They were small files. So what it did is that it merged all of them, and then it created an appropriately sized file. That's the first one. The second problem that it helps avoid is data skew. We've seen that we had partitions which had lots of data, and that is where this example came in, right? This was that example where one partition had a lot of data, and we also had this example where the partition 2023 was skewed, right? So what it did was that it divided this partition into appropriate number of parts, and that is how it avoided the skew problem. Now it's very important to note is that when we talk about skew, we think of it as there is one partition and it has tremendous amount of data to process, and for that reason it takes forever to process it, right? So this is avoided by dividing it into respective parts. But let's say you have a data set, it has 1 million keys for a particular value, right? So let's say there is a key, and for that key there are 1 million values, and when you do a join, the same keys go to the same partition in Spark, right? So it is going to create a skew again. Now I'm mentioning this in order to point out that liquid clustering doesn't change shuffle behavior, right? What it helps avoid is a skew at this point, right? It basically sizes the file appropriately so that all of the tasks get appropriately sized partitions, right? The sizes of the partitions that they get are not skewed. Okay, so now let's see liquid clustering in action. What I'm going to do is that I am going to create two tables. The first one I'm going to partition and Z-order by, and the second one I'm going to do a liquid clustering. And then let's run a query on both the tables and compare the runtime. Yeah. So let me quickly copy all of these paths. So this is going to be spark dot read dot parquet. Okay, this has been read in. Now let me union all of these files, all of these data frames. df2 dot union df3. Let's also select some relevant columns from here because we don't want to, there are too many columns in here. Customer ID, category, price, quantity, and the invoice date. Yeah. So now that this is done, let me go ahead and write this file, write dot mode overwrite dot partition by, let's partition by invoice date, something similar that we've done earlier. And let's save this file as delta catalog delta db dot liquid clustering example1. And let's now run a zorder on this file, delta catalog dot delta db dot example1 zorder by customer id. Yeah, because you remember we've done a similar, we've run a query where we filtered by customer id earlier, right? So for that reason I want to zorder by customer id, and then I'll run the same kind of query. Yeah. So just to quickly show you once again, I want to mimic this kind of a query which we've run earlier. Yeah, something like this, right? Let's go ahead and run this. Okay, so now this is the first table, and let's also do a count to make sure that we have data that has landed in over here. Yeah, let's run this. And parallelly, I'm also going to create another table, which is going to be example 2, and I am going to do a cluster by. And you remember that in cases where we have a partitioned and a z-ordered column, we basically take in both the partition and the z-ordered column as the cluster by column, right? So the partition column is invoice date, the z-order column is customer ID. So I'll basically put in both of these values over here. Yeah. So now let's go ahead and also run this. Okay, so there have been some significant optimization. It added 174 files and 364 files have been removed. So now let's have a look at the count. The count is 99457, and the count over here is just the same. So now let's go ahead and run this query, which is select category comma sum of price into quantity as total sales, right, as total sales from this table where customer ID equals 201, and we group by category, right? And I also want to time this query, so I'm going to do this inside a spark.sql. And let's put this over here. and let's go ahead and run this. Yeah, actually, let me also add in something else. Let me add in and invoice date between 20220101 and 20231231. The reason why I also added in this over here is because I want to test out both the columns, right? Because we are partitioning by invoice date and then we are ordering by the customer ID. Yeah. Okay, so this is complete and this took somewhere around 254 milliseconds. Now let's also run this on the other table and we see that this is 150 milliseconds, right? Not a very significant improvement, but still a good improvement, right? But we know that the data on which we are running is limited, right? So probably we'll be able to see these improvements on a larger scale when we run these operation on huge amounts of data, right? But overall, I believe that this gives you a gist of how liquid clustering works and how you can still compare when you use a partition by and a reorder and equivalently convert that to a cluster by. And there are definitely performance benefits that you get out of it, right? Okay, so now that we've seen liquid clustering in action, it's really important to understand that it cannot be used together with ZOrder or hive tile partitioning, right? So if you're using liquid clustering, that will independently be the mechanism for deciding the layout of your data. Yeah. So another question that you might have in mind is, how do I choose the liquid clustering column, right? The best practice is to choose the most frequently used column in your query filters, right? And if two columns are highly correlated, you should just include one of them in your query filter. Yeah. And what I mean by that is, actually, let me first quickly annotate. Let's say you have a column called product category. You have a column called product category and you have another column called location. And these two columns are, for whatever reason, they are highly correlated. So what it means is that whenever you choose a particular product, it is always going to yield the same location, right? If you choose another product, it is going to yield the same location always, right? So that means that there is no point including this column location. So in those cases, you remove the columns which are highly correlated. You remove location and you only go ahead with product category, right? So that's the first point. The second point is, if you're converting a table, an existing table, and it already has some kind of strategy, some kind of partitioning or the order strategy already being followed, and now you want to use liquid clustering, these are the rules that you should follow. So the first one is if it's already hive partition, basically just go ahead and use that partition column as the clustering key. The second one is if you're using a column for the order indexing, use the same ZOrder column for your clustering, right? The third one is hive style partitioning and ZOrder. We've seen this example, right? We've used both. We first partitioned by hive style partitioning, and inside of it, we've applied ZOrder. So there are two different columns. And in the previous example, we hive partitioned by invoice date, and then we ZOrdered by category, right? So in that case, use both the partition column and the ZOrder by column as your clustering key. So your new clustering key basically becomes invoice date and category. So you simply cluster by these two columns. And the last one is if you're using generated column to reduce the cardinality, for example, date or timestamp. So let's say you have a timestamp column and then you convert it to a date. Many times we do that in order to reduce the cardinality, right? So if we are already doing this and if we partition by date, in that case, use the original column. Just use the timestamp as your clustering key and don't create a generated column. So there's no need to create a date column, right? You just cluster by the timestamp. Yeah. So to quickly summarize, liquid clustering is going to be super helpful
when your query patterns are going to change down the line, right? You feel that your query patterns are going to change down the line, and you don't want to be bound by fixing the partitioning or the Z-order column, right? So liquid clustering helps you remain flexible. You have that flexibility of being able to change the cluster by columns anytime down the line, right? So that's the first benefit. The second benefit is it avoids the small file problem. As we've seen that it combines a lot of small files into appropriately sized files. It even breaks down bigger files, largely sized files, into appropriately sized one. Yeah. And the third one is it avoids data skew. It basically breaks up the bigger partitions into smaller ones, and that is how each task or each core gets a reasonable amount of data to process. I'm super happy to see that you've reached the end of the video, and I really hope that you learned a lot from it and you enjoyed it. So please don't forget to like and share this video, tag me on LinkedIn, share whatever you've learned. I'll be more than happy to see that. Please don't forget to subscribe to my channel, because I've seen that only 30% of you have subscribed to my channel. So please go ahead and hit that subscribe button. It really motivates me to make a lot more content. So thank you so much for watching.